The night sky seems so permanent, so unchanging. We look up and see the same stars our ancestors saw thousands of years ago, steady points of light that have watched over human history. But that steadiness is an illusion. The universe is constantly moving, constantly changing, and sometimes those changes happen fast enough that we can actually see them unfold before our eyes. Stars that have burned for millions of years can suddenly dim or flicker in ways that challenge everything scientists thought they knew. What looks eternal from down here is actually restless, unpredictable, and full of surprises. Even the brightest, most familiar stars can behave in ways that leave astronomers scratching their heads, reminding us that reality is far stranger and more complex than it appears. In this video, we'll explore one such mystery that unfolded recently, teaching us that even the sky above us is not as predictable as it seems. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. The red giant sitting in Orion's shoulder has been there, glowing quietly, for as long as humans have looked up at the night sky. This star, Betelgeus, has watched civilizations rise and fall, its ancient light traveling across hundreds of years just to reach our eyes tonight. And for most of that time, it behaved exactly as you'd expect a star to behave: steady, reliable, predictable. Stars like Betelgeuse occupy a strange place in our understanding of time. They seem permanent, unchanging, yet they're actually going through life cycles that span millions of years. This particular star is what astronomers call a red supergiant, meaning it's already lived through most of its stellar life, expanding into something almost unimaginably large. If you could somehow place Betelgeuse where our sun sits, it would swallow up Mercury, Venus, Earth, and Mars, possibly reaching all the way out to Jupiter's orbit. The scale becomes almost philosophical when you think about it. We spend our lives worrying about things that last days, weeks, maybe decades. Meanwhile, this giant ball of plasma has been burning through nuclear fuel for millions of years, slowly working its way toward an inevitable explosion that will someday light up our sky brighter than the full moon. But here's where the story gets interesting. Around late 2019, something unexpected happened. Betelgeuse started to dim, and not just a little bit. It faded to about 1/3 of its normal brightness, becoming noticeably fainter than stars it usually outshines. For people who know the night sky well, this was like watching a familiar landmark suddenly change. The dimming was dramatic enough that you could see it with your naked eye. Backyard astronomers started noticing first, then professional observatories turned their attention to Orion's shoulder. The measurements confirmed what observers suspected: this wasn't some trick of the atmosphere or an error in the instruments. Betelgeuse really was getting dimmer. Now, when a red supergiant starts acting strange, astronomers pay attention, because these are the kinds of stars that end their lives in spectacular explosions called supernovas. The possibility that Betelgeuse might be approaching its final moments created quite a stir. Headlines appeared. Social media buzzed with speculation. People started wondering if they were about to witness one of the most dramatic events in astronomy. The idea of a nearby supernova captures the imagination in a unique way. For a few weeks or months, we'd have what looks like a second sun in the sky, visible even during daylight. The explosion would pump out more energy in a few seconds than our sun produces in its entire 10 billion year lifetime. It's the kind of cosmic event that puts our daily concerns into a very different perspective. Scientists, however, approach the dimming with their usual methodical calm. Yes, a Betelgeuse supernova would be spectacular to observe, but at roughly 600 light-years away, it poses no threat to Earth. The distance is just right, close enough to put on an amazing show, far enough away to be completely safe. We'd get all the beauty and none of the danger. But the mystery remained. Why was this ancient star suddenly changing its behavior? The challenge with studying stellar surfaces is that most stars, even through our most powerful telescopes, appear as tiny points of light. You can analyze their light, measure their temperature, track their motion, but you can't actually see details on their surface, the way you might examine the Moon's craters or Mars's polar ice caps. Betelgeuse is different, though. Its combination of enormous size and relatively close distance makes it one of the few stars where astronomers have actually managed to create images of the surface. These aren't the kind of sharp photographs you might see of planets, but they're still remarkable. Fuzzy maps showing hot and cool regions across the star's face, bright spots, and dim areas that change over time. The surface of a red supergiant is a turbulent place. Massive convection currents carry hot material up from the interior, like bubbles in boiling water, but on a scale larger than planets. These convection cells create the bright and dark patches that telescopes can detect, and they're constantly changing, making the star's brightness fluctuate in complex patterns. But the 2019 dimming event was different from these normal fluctuations. It was too dramatic, too sustained, too unusual for the typical behavior of even a variable star like Betelgeuse. Astronomers needed to figure out what was causing such a significant change, and they had several theories to investigate. One possibility involved dust. Stars like Betelgeuse are constantly losing material from their outer layers, puffing gas and particles into space like a cosmic wind. If conditions were right, this ejected material could condense into dust clouds that would block some of the star's light from our perspective, similar to how clouds can dim the sun on a partly cloudy day. Another theory focused on the star's internal dynamics. The convection processes inside red supergiants are incredibly complex, and it's possible that some internal change could cause a temporary dimming. Perhaps a particularly large, cool region had formed on the star's surface, reducing the overall brightness in a way that would eventually reverse itself. As months passed, astronomers continued monitoring Betelgeuse carefully, gathering data from telescopes around the world and in space. Slowly, the star began to brighten again, gradually returning toward its normal luminosity. This recovery provided important clues about what had likely happened. The evidence eventually pointed toward the dust cloud explanation. Betelgeuse had apparently ejected a particularly large amount of material, which then condensed into dust particles that partially obscured our view of the star. As this dust cloud dispersed or moved away, the star's light reached us more freely again, and Betelgeuse returned to its familiar brightness. In a way, the whole episode illustrates something profound about scientific discovery. Here was a dramatic change in one of the sky's most recognizable stars, visible to anyone who looked up at Orion, yet understanding what was actually happening required sophisticated instruments, careful analysis, and months of patient observation. It also reminds us that even in our age of advanced astronomy, the universe still holds surprises. We can predict eclipses centuries in advance, track asteroids with incredible precision, and detect planets around distant stars, but a nearby giant star can still puzzle us with unexpected behavior. The Betelgeuse dimming event has also taught astronomers valuable lessons about how red supergiants lose material in their final stages of life. This mass loss is a crucial part of stellar evolution, affecting how these massive stars will eventually explode and what elements they'll scatter into space when they do. When Betelgeuse does finally reach the end of its life, whenever that might be, it will contribute to the cosmic recycling program that has been running for billions of years. The heavy elements forged in its core, carbon, oxygen, silicon, iron, will be blasted into space, eventually becoming part of new stars, new planets, maybe even new forms of life. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of these came from ancient stars that lived and died long before our solar system existed. There's something both humbling and comforting about this connection. We're made of star stuff, as Carl Sagan famously put it. But more than that, we're temporary arrangements of atoms that have been cycling through the universe for billions of years, taking part in a story much larger and longer than any individual life. When astronomers point their telescopes at Betelgeuse, they don't see a perfect sphere of light. Instead, they capture something more complex, a slightly irregular glowing disk that shifts and changes over time. This massive red supergiant isn't the smooth, steady star you might imagine from looking up at Orion on a clear night. During the famous dimming event that captivated scientists worldwide, something remarkable appeared in the images. When researchers compared photographs taken before and during the brightness drop, they discovered that a large section of the star looked noticeably darker than the rest. It was as if someone had cast a shadow across part of Betelgeuse's surface. This observation opened up several fascinating possibilities. One explanation involved the star ejecting enormous clouds of gas and dust into space. Picture a bright lantern surrounded by drifting smoke. The lantern burns just as brightly as before, but the smoke dims its glow when you view it from certain angles. In Betelgeuse's case, this expelled material could cool and condense into tiny particles, creating a veil that blocks some of the star's light. But there's another intriguing possibility that has to do with the star's surface itself. Red supergiants are anything but calm. Their surfaces boil and churn with massive convection currents, each one larger than Earth's entire orbit around the Sun. These rising and falling regions of hot gas create bright and dark patches that shift slowly across the star's face over time. Think about it this way: if one of these darker regions grew large enough, it could reduce the star's apparent brightness, at least temporarily. It's like watching storm clouds move across a massive glowing landscape in space. As scientists gathered more data, the evidence began pointing toward a combination of both effects. Betelgeuse likely experienced a massive outflow of material that cooled and formed dust, while its already complex surface continued its restless shifting and pulsing. Yet even with these explanations, something curious remains about the timing and scale of what happened. The dimming was deeper than most researchers expected from ordinary stellar behavior. It wasn't entirely unprecedented, but it was unusual enough to spark intense scientific study worldwide. This is where the story becomes even more captivating, because Betelgeuse isn't just dimming and brightening in simple, predictable cycles. This star exists in a profoundly unstable stage of its life, constantly shedding mass, pulsating and evolving in ways that challenge our ability to predict exactly what will happen next. Stars like Betelgeuse live remarkably fast lives compared to smaller stars like our Sun. They burn through their nuclear fuel at an incredible rate, changing their internal structure over relatively short astronomical timescales. Deep inside the star, different layers fuse heavier and heavier elements, building an onion-like interior of distinct fusion zones, each one producing energy in its own unique way. These internal processes profoundly affect the star's outer layers, causing it to expand, contract, and sometimes violently eject vast shells of gas into space. Over thousands of years, Betelgeuse has surrounded itself with a complex environment made entirely of its own previously expelled material, a kind of slow-moving fog of the star's own creation. When new eruptions occur, they interact with this existing environment, creating intricate patterns that can be extremely difficult to interpret from our distant vantage point on Earth. It's like trying to understand a conversation by watching shadows on a wall. So when Betelgeuse dimmed, scientists weren't just observing a single, isolated event. They were witnessing part of a long, intricate process that has been unfolding for millennia and will continue for thousands of years more. The dimming was just one chapter in an epic story of stellar evolution. Even now, months after the initial dimming, the star has partially recovered its brightness, but it hasn't returned exactly to its previous behavior. Its cycles of brightening and dimming appear slightly altered. Its surface continues to show subtle changes that keen observers monitor night after night. Observatories around the world continue their patient vigil, gathering data continuously, trying to decode what these variations reveal about the final stages of massive stellar lives. Because that's the deeper significance of Betelgeuse. It's not just an astronomical curiosity hanging in our winter sky. This star serves as one of our best natural laboratories for studying how massive stars end their lives. And that matters tremendously, because supernovae rank among the most important events in the entire universe. These cosmic explosions create many of the heavy elements that make up planets, oceans, and even the iron flowing through your bloodstream right now. Long before Earth existed, ancient stars exploded and scattered these essential elements into space, seeding the vast molecular clouds from which our solar system eventually formed billions of years later. In a very real sense, understanding stars like Betelgeuse helps us understand our own cosmic origins. There's something deeply comforting about the night sky when you observe it regularly over time. Familiar patterns repeat themselves with seasonal precision. Constellations return like old friends. Stars hold their appointed places night after night, year after year, as if they've made some cosmic agreement to remain steady so we can learn to recognize them. Even the wandering planets follow predictable paths once you understand their celestial choreography. Astronomers have always depended on this fundamental reliability. Much of science itself depends on it. When objects behave consistently over long periods, patterns emerge naturally, and patterns are the foundation of understanding. That's precisely why Betelgeuse captured everyone's attention when it began behaving differently. For most of recorded human history, this red supergiant had been steady in exactly the way astronomers expected a star of its type to be steady. This doesn't mean it never changed, of course. Betelgeuse has always been what researchers call a variable star, meaning its brightness rises and falls over time, but those changes followed rhythms that were familiar and measurable, cycles that could be tracked and anticipated with reasonable accuracy. It was like listening to a favorite piece of music. The notes rose and fell in expected ways, but the underlying melody remained comfortingly recognizable. Then, in late 2019, that familiar melody suddenly changed. Observers who routinely monitored stellar brightness as part of ongoing surveys noticed that Betelgeuse appeared dimmer than usual. At first, the change was subtle enough that it could have been dismissed as part of the star's ordinary variability. But the dimming continued night after night, and careful measurements consistently showed the same troubling trend. Astronomy maintains a long, proud tradition of careful patience and methodical verification. Scientists don't typically jump to dramatic conclusions based on limited data. Instruments can malfunction unexpectedly. Atmospheric conditions can distort even the most careful observations, and data must always be confirmed from multiple independent sources before anyone suggests that something truly unusual might be happening. So telescopes in different parts of the world turned their attention toward Orion. Professional observatories compared their measurements carefully. Amateur astronomers, some using sophisticated equipment in their own backyards, contributed valuable observations as well. One of astronomy's quiet strengths lies in the fact that many important discoveries emerge not from single dramatic moments, but from the steady accumulation of careful, patient watching over extended periods. And in this case, all the data agreed completely. Betelgeuse was dimming at an unprecedented rate. By early 2020, the star had dropped to roughly 1/3 of its normal brightness. To put that dramatic change into perspective, imagine a lighthouse that had shone steadily for centuries, suddenly fading until it was barely visible through evening mist. Not completely gone, not entirely extinguished, but clearly changed in a way that demanded immediate scientific attention. The night sky itself seemed subtly altered to anyone familiar with winter constellations. People who knew Orion well could see the difference without any instruments at all. The hunter's distinctive shoulder no longer stood out as prominently as it once had, creating an eerie sense that something fundamental had shifted in the cosmic order. This wasn't just a matter for specialists anymore. The story began spreading far beyond professional observatories and into public consciousness. Newspapers and science magazines started asking the same compelling question in various forms. Was Betelgeuse preparing to explode in a spectacular supernova? The question seemed perfectly reasonable, given what we know about red supergiants and their ultimate fate among the stars. When we look up at Betelgeuse in the winter sky, we're seeing something remarkable. A star so massive, so energetic, that it defies almost everything we think we know about normal stellar behavior. This red supergiant burns through its fuel at such an incredible rate that in cosmic terms, it's living life in the fast lane. The surface of Betelgeuse churns constantly. Imagine convection cells, like bubbles in boiling water, but each one large enough to swallow Earth's entire orbit around the Sun. These massive currents carry material up from the depths, then let it cool and sink back down. It's a process so violent, so dynamic, that the star itself appears to pulsate and change brightness over time. For decades, astronomers tracked these changes. They found patterns, cycles that repeated every few hundred days, others that took years to complete. The star had its rhythms, predictable in their own chaotic way. But then, something changed. In late 2019, Betelgeuse began to dim. Not gradually, not following any known pattern, but dramatically. Within months, it had lost more than half its brightness. For the first time in recorded history, this star that had been a reliable beacon in Orion's shoulder became noticeably fainter to the naked eye. The implications were staggering. If Betelgeuse were about to explode as a supernova, the event would be visible during the day. For weeks, perhaps months, we'd have a second moon-bright object in our sky. The energy release would be so immense that ancient civilizations would have recorded it as a divine event. But here's where science teaches us patience. When astronomers say a star is nearing the end of its life, that could still mean tens of thousands of years. In human terms, that's longer than all of recorded civilization. In cosmic terms, it's barely a blink of an eye. Time, it seems, is all about perspective. So scientists has asked a more immediate question. What exactly was happening right now? They turned to spectroscopy, breaking the star's light into its component colors. What they found was puzzling. The star's temperature hadn't dropped nearly enough to explain the dramatic dimming. Betelgeuse was still producing almost the same amount of light as before. Something was blocking it. The answer, it turned out, was dust. Red supergiants like Betelgeuse constantly shed material from their outer layers. Gravity holds these layers only loosely, and the powerful convection currents can push matter out into space. When this material cools, it forms tiny grains, similar to sand or soot, but spread across vast distances. Advanced telescopes using interferometry, a technique that combines light from multiple mirrors, began to reveal the truth. Images of Betelgeuse's surface showed that part of the star appeared darker than the rest, not uniformly dim, but patchy, as if a veil had been drawn across one section. The star had essentially created its own dust cloud, which drifted between us and the stellar surface. This discovery revealed something profound about stellar death. These massive stars don't simply burn steadily until they explode. They go through dramatic episodes, shedding layers, creating clouds of material that will eventually become part of the interstellar medium. In a sense, Betelgeuse was already beginning to distribute the heavy elements it had created through nuclear fusion, seeding space with the building blocks of future planets and life. Deep inside the star, a complex drama was unfolding. Unlike our Sun, which burns hydrogen steadily in its core, Betelgeuse had long ago exhausted its hydrogen fuel. Now it was fusing heavier elements in a series of concentric shells. Each layer burned different fuel at different rates, creating an inherently unstable structure. The balance between gravity, pulling inward, and fusion pressure, pushing outward, became increasingly delicate. This layered burning creates a dynamic system, where small changes deep inside can have dramatic effects on the surface. It's like a complex engine with multiple moving parts, where adjusting one component affects everything else. The outer layers respond to these internal changes by expanding, contracting, and sometimes erupting material into space. By mid-2020, Betelgeuse began to brighten again. Slowly, almost tentatively, it returned toward its former luminosity. The dust cloud that had caused the dimming gradually dispersed or moved out of our line of sight. But the star's behavior didn't return entirely to normal. Its brightness cycles appeared slightly altered, as if it had settled into a new rhythm. This lingering change suggested that the dimming wasn't just a temporary disturbance. It might have been part of a larger shift in the star's structure, possibly indicating changes in the fusion processes occurring in those deep layered shells. For astronomers, this was invaluable data about a phase of stellar evolution that's normally impossible to study in detail. Most supernovae are too distant for us to monitor the star beforehand. By the time we detect the explosion, it's already over, and scientists must piece together what happened from the aftermath. Betelgeuse offers something rare: a front row seat to watch a massive star in its final evolutionary stages in real time. Every unusual fluctuation provides insights into how stars many times more massive than our Sun live and die. These observations help refine our models of stellar evolution, but they also remind us of something deeper. The universe is constantly changing, even in ways too slow for human perception. The materials that make up our bodies, the oxygen we breathe, the calcium in our bones, the iron in our blood, all were forged inside stars like Betelgeuse. When these massive stars eventually explode, they scatter these elements across space, where they become incorporated into new stars, planets, and eventually, living things. In studying Betelgeuse's dramatic dimming, we weren't just watching a distant star shed some dust. We were witnessing part of the cosmic cycle that connects us to the universe itself. The same physical processes that caused this temporary dimming will eventually distribute the star's contents across space, contributing to future generations of stars and worlds. Perhaps there's something humbling about realizing that our existence depends on the death throes of ancient stars. Every element heavier than hydrogen in our bodies was created in stellar cores or supernova explosions. We are, quite literally, made of star stuff, carrying within us the legacy of cosmic events that occurred billions of years ago. The story of Betelgeuse continues to unfold. Astronomers keep monitoring its brightness, tracking its cycles, waiting to see what this massive star will do next. Whether it explodes tomorrow or in 50,000 years, it has already taught us valuable lessons about stellar evolution and our place in the cosmic order. The universe operates on timescales that make human existence feel like a brief flicker, yet even the most ancient celestial objects are not frozen in time. Stars, which seem permanent and unchanging from our perspective, are actually in constant motion, evolving over periods that span millions of years. This cosmic ballet unfolds so slowly that we rarely notice it, but occasionally, a star reveals its dynamic nature within the span of a human lifetime, reminding us that nothing in the universe is truly static. When we consider the vastness of space and time, it becomes clear that our understanding of permanence is deeply flawed. The stars that guided ancient navigators were subtly different from the ones we observe today, and the ones our descendants will see will have changed again. This constant transformation happens everywhere in the cosmos, from the smallest particles to the largest galaxies, following laws of physics that govern all matter and energy. One particular star has captured the attention of astronomers precisely because its changes have become visible to us within our brief lifespans. This red supergiant, sitting prominently in the winter constellation of Orion, challenges our assumptions about stellar behavior and offers us a window into processes that typically remain hidden across cosmic time. The sheer scale of this star defies easy comprehension. If we could somehow replace our Sun with this giant, the inner planets of our solar system would simply cease to exist, consumed within its vast atmosphere. Mercury and Venus would disappear entirely, while Earth's orbit would lie deep within layers of glowing gas. The star stretches outward beyond Mars, possibly reaching toward Jupiter. Depending on how we measure its diffuse outer boundaries, this enormous size comes not from exceptional mass, but from the star's advanced age and the peculiar way massive stars evolve. During most of a star's life, it maintains a delicate balance between gravity pulling inward and nuclear fusion pushing outward. This equilibrium keeps the star relatively stable and compact. However, when the hydrogen fuel in the core begins to run out, everything changes dramatically. The core contracts and heats up, while the outer layers expand outward like a slowly inflating balloon. The surface cools as it expands, shifting from white-hot to a deep red glow. But the total energy output remains staggering because of the star's immense size. Even with a relatively cool surface, the sheer area radiating energy means this star shines with tens of thousands of times the brightness of our Sun. What makes this giant particularly fascinating is its fragile nature. Despite its enormous size, the outer layers are held together by surprisingly weak gravity. The star is so large and diffuse that someone standing, somehow in its outer atmosphere, would barely feel any gravitational pull at all. Instead, they would witness massive currents of gas, rising and falling in slow motion, like weather systems that dwarf entire planets. These convection currents are not small ripples on the surface. While our Sun has convection cells roughly the size of continents, this red giant hosts bubbles of hot gas, larger than Earth's entire orbit around the Sun. A single convection cell might take months or years to complete one cycle of rising, cooling, and sinking back down, creating an ever-changing pattern of bright and dark regions across the star's face. This constant churning means the star's surface is never uniform or smooth. Bright spots and darker areas drift slowly across its face, like enormous glowing continents, causing the star's brightness to fluctuate naturally over time. These variations have puzzled and intrigued astronomers for decades, providing clues about the complex physics governing such massive objects. The star's relatively close distance of roughly 600 light-years makes it an exceptional subject for study. Most stars are too far away and appear too small for us to see any surface details, even with our most powerful telescopes. This giant is one of the rare exceptions, close enough and large enough that we can actually observe features on its surface directly. This proximity also creates an interesting perspective on time and light. The photons reaching our eyes tonight began their journey around the time Galileo first pointed a telescope at the sky. We are not seeing the star as it exists now, but as it appeared centuries ago. This time delay connects us to history in a tangible way, making the star feel both ancient and surprisingly accessible. The reddish glow that makes this star distinctive has been noticed by humans for thousands of years. Long before anyone understood what stars actually were, observers noticed that one light in Orion looked different from the others. Most stars shine with sharp white or bluish light, but this one carried a subtle reddish tint, like a glowing coal seen from across a dark room. This red color tells us about the star's temperature and composition. As stars age and expand, their surface temperatures drop, shifting their color from blue-white to yellow to red. The red glow indicates a surface temperature much cooler than our sun's, despite the star's enormous energy output. It's a visible sign of the star's advanced evolutionary stage, a cosmic sunset that signals the approaching end of its life. Modern astronomy has revealed that this star is not just large and old, but also unstable in ways that make it particularly interesting to study. Its brightness varies unpredictably, sometimes dimming dramatically, before returning to normal levels. These changes happen over months or years, fast enough for astronomers to observe and analyze in detail. Each fluctuation provides new data about the star's internal structure and behavior. By measuring how the brightness changes and mapping the surface features, scientists can test their theories about stellar evolution and the complex processes that occur inside massive stars. These observations have implications far beyond understanding a single object in space. The elements that make up planets and life itself are forged inside stars like this one. During their lifetimes, massive stars create and scatter heavy elements throughout space, enriching the cosmic environment with the raw materials needed for rocky planets and biological processes. When we study this red giant, we are learning about the factories that produce the very atoms in our bodies. The star's eventual fate is both dramatic and scientifically important. Stars of this size do not simply fade away like smaller stars. Instead, they end their lives in spectacular supernova explosions that can outshine entire galaxies for weeks or months. These explosions scatter newly formed elements across vast regions of space, seeding future generations of stars and planets. The timing of this cosmic event remains uncertain. The star could explode tomorrow, or it might continue in its current state for thousands of years. From our perspective, both timescales are brief, but the uncertainty adds to the star's mystique and scientific value. Whenever it happens, the explosion will be visible from Earth even during daylight, creating a temporary new star in our sky. This unpredictability reflects a deeper truth about the universe. Despite our growing knowledge and sophisticated instruments, nature still holds surprises. Even objects we have studied for decades can behave in unexpected ways, humbling our confidence and pushing us to refine our understanding. The cosmos operates according to physical laws, but the complexity of those interactions often produces results that challenge our predictions. There is something profound about watching a star that has burned for millions of years continue to surprise us. It reminds us that the universe is not a static backdrop for human activity, but a dynamic, evolving system where change happens on every scale. From the quantum fluctuations in empty space to the slow dance of galaxies, nothing remains exactly the same from one moment to the next. This perspective transforms how we think about our place in the cosmos. We are not separate observers looking at a distant universe, but participants in an ongoing story of stellar evolution, element formation, and cosmic change. The calcium in our bones and the iron in our blood were created inside stars like this one, making us direct products of stellar alchemy. The study of this red giant also demonstrates how astronomy connects us to both the past and the future. The light we see tonight carries information from centuries ago, while the star's eventual explosion will influence the formation of new stars and planets millions of years from now. We occupy a brief moment in this vast timeline, but our observations contribute to humanity's growing understanding of cosmic processes. Each measurement of the star's brightness, each map of its surface features, and each analysis of its spectrum adds to our knowledge of how massive stars behave. This information helps astronomers understand similar objects throughout the galaxy and refine their models of stellar evolution. The work being done today will inform our children's understanding of the universe and guide future discoveries. The philosophical implications are equally compelling. Here is an object so large that it challenges our intuition about size and scale, yet so distant that we see it only as a point of light. It burns with the energy of tens of thousands of suns, yet its outer layers are held together by gravity so weak that they barely cling to the star at all. These contradictions remind us that the universe operates by rules that often defy common sense. Perhaps most remarkably, this giant star serves as a reminder that even the most fundamental seeming aspects of our universe are temporary. Stars are born, evolve, and die, just like living creatures, but on timescales that make human history seem instantaneous. What we consider permanent fixtures of the night sky are actually dynamic, changing objects caught in a brief moment of cosmic time. This impermanence extends to everything around us. The elements in our planet, the energy from our sun, and even the space between galaxies are all products of processes that began billions of years ago and will continue long after human civilization has ended. We are temporary arrangements of matter and energy, borrowing atoms from the universe for a brief time before returning them to the cosmic recycling process. Yet this temporal nature does not diminish our significance. Instead, it highlights how remarkable it is that the universe has evolved in such a way that parts of it can become aware of the whole. Through human consciousness and scientific inquiry, the cosmos has developed the ability to study and understand itself. We are the universe looking back at its own history and forward to its own future. When we look up at the stars on a clear winter night, we're seeing light that began its journey years, decades, or centuries ago. Each point of light carries stories of processes so vast and complex that they challenge our everyday understanding of time and change. Stars aren't just distant suns, they're cosmic factories, forging the very elements that make up planets, and ultimately, life itself. Consider a red supergiant star, one of those massive stellar giants that dwarf our own sun by hundreds of times. These enormous stars are constantly shedding pieces of themselves into space. Like a slow-motion explosion that unfolds over thousands of years, streams of gas flow away from their surfaces, carrying carbon, oxygen, nitrogen, all the building blocks of future worlds. It's a kind of stellar generosity, really this gradual sacrifice of material that will one day become new stars, new planets. What's fascinating is how this process connects the death of one star to the birth of countless others. The gas and dust expelled from these giants doesn't just disappear, it drifts through space, eventually gathering in vast molecular clouds. These clouds can stretch for hundreds of light years, floating in the cosmic darkness, waiting. They're stellar nurseries, though they don't look like much to our eyes, just empty regions of space. But gravity never stops working, even in the coldest, most diffuse corners of the universe. Over millions of years, slight variations in density cause parts of these clouds to begin collapsing inward. The process starts slowly, almost imperceptibly, but acceleration is inevitable. As material falls toward a central point, it compresses and heats up, eventually forming what astronomers call a protostar. At this stage, you have an object that glows faintly from the heat of compression, but it's not yet a true star. Nuclear fusion hasn't begun. That requires temperatures of millions of degrees, pressures that exist nowhere else in nature, except in the cores of stars themselves. But as more material continues to fall inward, that critical threshold is eventually reached. Hydrogen nuclei begin fusing into helium, and suddenly, a new star ignites. This moment marks the beginning of what scientists call the main sequence, the longest and most stable period in any star's life. During this phase, the star achieves a delicate balance. Gravity pulls inward, trying to compress everything into a tiny point. Nuclear fusion pushes outward with tremendous force. These opposing forces reach equilibrium, and a star shines steadily for millions or billions of years. Our own sun is currently in this stable phase, and has been for about 4.5 billion years. It's a comforting thought, this stellar reliability, this cosmic predictability. But not all stars are created equal, and the most massive ones live very different lives. When a star is born with much more mass than our sun, everything happens faster and more dramatically. These stellar giants burn through their nuclear fuel at enormous rates, shining brilliantly but briefly. Where our sun will remain stable for billions more years, the most massive stars exhaust their fuel in just a few million years, a blink of an eye in cosmic terms. And when such stars begin to age, they become restless, unpredictable. Their outer layers expand and cool, turning them into red supergiants, enormous and unstable. They pulsate, they vary in brightness, they throw off material in great eruptions. They're no longer the steady, reliable fusion reactors of their youth, but rather chaotic, complex systems that challenge our understanding. Sometimes these aging giants catch our attention in unexpected ways. When a star that's been shining steadily for generations suddenly changes its behavior, astronomers take notice, not because stellar change is unusual, quite the opposite, but because most changes in stars happen so slowly that we don't notice them in human lifetimes. Stars operate on geological timescales, cosmic timescales, even dramatic events unfold over centuries or millennia. So when a change becomes visible within months or years, it's genuinely surprising. It's like watching erosion happen in fast forward, seeing processes that usually take forever compressed into moments we can actually observe. This is what makes certain stellar observations so compelling. When familiar stars alter their appearance noticeably, it forces us to look more carefully than we ever have before. Telescopes around the world turn toward such objects, space observatories join the investigation, and spectrographs begin analyzing every photon of light. Modern astronomy has given us tools that would seem magical to earlier generations. Interferometers can combine signals from multiple telescopes, achieving resolutions that were once impossible. We can measure the motion of gas flowing away from stellar surfaces, track the expansion and contraction of outer layers, study temperature variations across stellar disks. Each observation reveals more detail about how these immense restless objects live and evolve. Yet even with all our sophisticated instruments, individual stars often surprise us. They have personalities of their own, shaped by rotation rates, internal mixing patterns, magnetic fields, subtle differences in composition. The truth is, stellar evolution models can describe general patterns, but they can't predict every detail of how a specific star will behave. Stars are simply too complex, too layered, too turbulent. Their interiors are vast engines of nuclear reactions and convective motion, operating on scales that challenge both observation and theory. From our distant vantage point, we see only the outermost layers of these objects, the thin, glowing surfaces that radiate light into space. What happens deep inside, in the cores where fusion continues or begins to fail, remains hidden. We can infer processes through models and indirect measurements, but the star's interior keeps its secrets. Sometimes, though, the surface offers hints that something deeper is changing. Fluctuations in brightness, eruptions of gas, variations in temperature, these are all signs of internal processes we can't directly observe. They're messages from the hidden heart of the star, written in the language of light and motion. For the most massive stars, these changes are part of a slow, complex journey toward an inevitable conclusion. Nuclear fuel doesn't last forever, not even in the most enormous stars. One day, the delicate balance between gravity and fusion will collapse. The core will fall inward, rebound, and drive a shock wave outward in one of the most powerful explosions in the universe. This is stellar death as cosmic spectacle, the supernova explosion that can briefly outshine an entire galaxy. It's the final act in the life of a massive star, and also the beginning of something new. The explosion scatters heavy elements across vast distances, seeding space with the materials needed for planets and life. There's something profoundly moving about this cycle, this transformation of stellar death into the seeds of future creation. It connects us to the stars in ways that pure science alone can't capture. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was forged in the nuclear furnaces of ancient stars and scattered by their explosive deaths. We are, quite literally, made of star stuff, participants in a cosmic recycling program that's been running for billions of years. Every atom in our bodies has a stellar pedigree, a history that stretches back to the deaths of massive stars that exploded long before our solar system existed. This perspective changes how we think about our place in the universe. We're not separate from the cosmos. Observing it from the outside, we're part of it, temporary arrangements of stellar material that have somehow learned to contemplate the stars that made us possible. And when we look up at the night sky, when we notice a star changing its behavior or varying its brightness, we're witnessing the ongoing processes that connect past, present, and future. The light reaching our eyes began its journey in nuclear furnaces, operating at temperatures of millions of degrees, traveled across space for years or centuries, and ended its journey on the retina of a creature made from the ashes of ancient stars. It's a chain of connection that spans time and space, linking the microscopic quantum processes in stellar cores to the largest structures in the universe. And sometimes, if we're patient enough, if we watch carefully enough, we get to witness small chapters in this vast story unfolding in real time. The universe operates like a vast clockwork, but with timepieces that run at completely different speeds. Our sun, that steady beacon we depend on, represents what astronomers call the main sequence phase. It's been burning hydrogen in its core for about 4.5 billion years now, maintaining this delicate balance between the crushing force of gravity trying to squeeze it inward and the explosive pressure from nuclear fusion pushing outward. This cosmic dance will continue for roughly another 5 billion years before anything dramatic happens. But here's where things get fascinating. Not every star follows the same schedule. Think of it like different types of fires. Some burn low and steady, others rage intensely and consume their fuel quickly. Massive stars, the true giants of the cosmos, live life in the fast lane. They're many times heavier than our sun, and this extra mass creates incredible pressure and heat in their cores. The nuclear reactions happen much faster, much more violently. A star like Betelgeus, that famous red shoulder of the constellation Orion, might only live for 10 million years from birth to death. Now, 10 million years sounds impossibly long to us, but in cosmic terms, it's practically a blink. Compare that to our sun's expected lifetime of about 10 billion years, and you start to see the difference. It's like comparing a thin birthday candle that burns all evening to a thick torch that blazes brilliantly but dies out in minutes. These massive stars burn hot and bright, but they pay for it with shortened lifespans. Eventually, inevitably, the hydrogen fuel in the core runs out. When this happens, the careful balance that's kept the star stable begins to shift. Gravity, that relentless inward pull, starts winning the battle. As the core begins to contract under its own weight, something interesting happens. The compression heats things up again, and the star's outer layers respond by expanding outward. This marks the beginning of what we call the giant phase. For stars similar to our sun, this creates a red giant, but for the real monsters like Betelgeuse, the expansion is far more dramatic, producing what we call a red supergiant. These are among the largest single objects in the universe. If you could somehow place Betelgeus where our Sun sits, its surface would extend past the orbit of Mars. The scale is almost impossible to comprehend. During this giant phase, the star's core becomes hot enough to fuse helium into heavier elements like carbon and oxygen. If the star is massive enough, the process continues, creating a kind of cosmic forge. Neon, magnesium, silicon, and eventually iron all get manufactured in the star's interior. Scientists often compare this to an onion, with different layers fusing different elements at different depths. Each shell contributes energy, but the whole system becomes increasingly complex and unstable. It's like a house of cards getting taller and more precarious with each addition. Iron represents a crucial turning point in this story. Every element lighter than iron releases energy when fused together, and this energy helps support the star against gravity's relentless pull. But iron is different. Fusing iron actually requires energy rather than producing it. Once the core becomes dominated by iron, the star's fate is sealed. The end, when it comes, happens with shocking speed. The core collapses in less than a second, falling inward at incredible velocity. When this collapse suddenly halts, the rebound sends a massive shock wave racing outward through all the star's layers. This is a supernova explosion, one of the most energetic events in the universe. For a brief moment, this dying star can outshine an entire galaxy containing hundreds of billions of other stars. But perhaps more importantly for the bigger cosmic story, this explosion scatters all those heavy elements the star created during its lifetime. These materials enrich the surrounding space, providing the raw ingredients for future generations of stars, planets, and eventually, life itself. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was forged in the nuclear furnaces of dying stars and scattered across space by supernova explosions. There's something profoundly humbling about that connection. For a long time, Betelgeuse seemed to be following this expected script perfectly. Astronomers could measure its mass, temperature, and evolutionary stage with reasonable confidence. Computer models suggested it had already burned through the hydrogen in its core and was now fusing heavier elements in shells around a contracting center. Its enormous size and distinctive reddish color fit perfectly with our understanding of red supergiants approaching the end of their lives. Nothing about Betelgeuse seemed particularly unusual, at least in broad terms. But even within this predictable framework, there's room for individual personality. Stars aren't identical copies of each other. Differences in how fast they rotate, what they're made of, and how materials mix in their interiors can alter the details of their evolution. Some stars lose mass more rapidly than others. Some pulsate more dramatically. Some develop complex magnetic fields that influence how gas flows in their outer layers. Betelgeuse, as astronomers have discovered, is one of the more restless examples. Its outer layers are only loosely held by gravity, and it constantly sheds material into space at a remarkable rate. Streams of gas flow outward like a stellar wind, forming vast, slowly expanding clouds around the star. At the same time, the star itself breathes like a living thing, expanding and contracting in regular cycles. These pulsations change its brightness by noticeable amounts even under normal conditions. For decades, observers carefully tracked these variations, identifying patterns that repeated every few hundred days, so variability itself wasn't surprising. What caught everyone's attention was the scale and suddenness of the dimming that began in late 2019. Most stars are remarkably predictable. Our Sun, for instance, varies in brightness by only a tiny fraction over its 11-year activity cycle. Even stars, known for their variability, usually follow patterns that can be described with mathematical precision. But Betelgeuse seemed to break its usual rhythm. Its brightness dropped far more dramatically than expected, and the timing didn't match any known cycle. It was like a metronome that had kept perfect time for years, suddenly missing several beats. This raised the intriguing possibility that something more than ordinary pulsation was happening. One explanation involved dust formation. If the star had expelled an unusually large amount of material that cooled and condensed into tiny grains, those particles could act like a cosmic fog, obscuring the light reaching Earth. In this scenario, the dimming wouldn't reflect any change in the star's actual energy output, just a temporary veil between us and the star. Another possibility involved changes in the star's surface temperature or structure. Massive convection cells, like enormous bubbles of hot gas rising and cool gas sinking, could create extended cool regions that would appear dimmer from our perspective. Both explanations fit comfortably within our general understanding of how red supergiants behave, but the combination and intensity of effects seemed unusually strong, and that's what made Betelgeuse such a compelling subject for study. While astronomers understand the broad outline of stellar evolution quite well, the detailed processes in the final stages of massive stars remain somewhat mysterious. Observations of stars like Betelgeuse provide rare opportunities to test our theories against reality. It's one thing to simulate a red supergiant's behavior on a computer. It's quite another to watch an actual star changing in real time, revealing secrets about processes we can only guess at. Betelgeuse is particularly valuable for another reason: its relative proximity to Earth. Many red supergiants are located thousands or tens of thousands of light years away, making detailed observation extremely difficult. But Betelgeuse, at roughly 600 light-years distance, is close enough that modern instruments can study its surface directly. This proximity allows astronomers to measure temperature variations across the star's face, track the movement of gas in its atmosphere, and detect the formation of dust clouds with unprecedented detail. Each observation adds another piece to the puzzle of how these cosmic giants live and die. When massive stars approach the end of their lives, they begin to shed their outer layers in ways that astronomers are still trying to fully understand. These colossal giants, burning through their nuclear fuel at tremendous rates, eventually reach a point where their cores can no longer sustain the energy needed to keep them stable. The mass loss that occurs during this phase happens through powerful stellar winds and violent ejections of material. Each observation of these processes adds another piece to our understanding of how stars behave. In their final chapters, yet even with decades of careful study, predicting the exact timing of a stellar explosion remains one of astronomy's greatest challenges. The scales involved stretch far beyond human experience. A star might appear unchanged for hundreds of years, then transform dramatically in just a few decades. This unpredictability reminds us that we're dealing with systems of almost incomprehensible complexity. The elements flowing through your bloodstream right now, the calcium in your bones, the iron that carries oxygen through your body, all of these were created inside ancient stars that died billions of years ago. When we observe distant stellar giants, we're not just looking at faraway objects, we're witnessing the very processes that made our existence possible. Betelgeuse, that familiar red star sitting on Orion's shoulder, had been a reliable presence in the winter sky for generations. Astronomers have tracked its brightness variations for more than a century, learning its rhythms, understanding its cycles. Some variations lasted weeks, others stretched across months, but all of them fell within predictable ranges. This kind of consistency builds a quiet confidence among observers. The story of Betelgeuse's dramatic dimming began not with headlines, but with routine measurements. In late 2019, astronomers monitoring variable stars noticed something subtle. The star appeared just slightly fainter than expected for that particular point in its known cycle. The difference was small, barely noticeable, the kind of variation that could easily be explained by normal stellar pulsations. But as days turned into weeks, the brightness continued to drop. What started as a minor curiosity became something worth watching more closely. Observatories increased the frequency of their measurements. Amateur astronomers, scattered across the globe, began reporting their observations to organizations that track stellar variability. This collaboration between professional astronomers and dedicated volunteers creates a monitoring network that operates around the clock. By December 2019, the dimming had become visually apparent. Anyone familiar with Orion could see that something had changed. The red star that normally dominated the constellation's shoulder now appeared noticeably fainter. Nearby stars that usually seemed dimmer by comparison appeared almost equally bright. For the first time in living memory, the night sky itself looked subtly different. This visibility made the event feel immediate in a way that most astronomical phenomena do not. You didn't need expensive equipment or specialized knowledge. A clear night and a few minutes of patient observation were enough to witness this cosmic transformation. Meanwhile, astronomers began analyzing the star's light spectrum in greater detail. These measurements revealed something important. Betelgeus's surface temperature had not dropped enough to account for the dramatic decrease in visible brightness. This suggested that the star was still producing roughly the same amount of energy and that something else was preventing that light from reaching Earth. If the entire star were cooling down, it might indicate deep structural changes, possibly even processes related to stellar death. But if something were blocking or scattering the light, the explanation could be quite different. Observations across different wavelengths provided additional clues. Infrared measurements, which detect heat and dust, suggested the presence of a material cloud surrounding the star. Dust grains have a peculiar property. They absorb and scatter visible light efficiently while allowing infrared radiation to pass through relatively unimpeded. This creates exactly the kind of effect that astronomers were observing, but confirming the presence of such a dust cloud required actually imaging the star's surface. Even the largest stars appear incredibly tiny from Earth's perspective. Resolving details on their surfaces requires extremely sophisticated techniques. Interferometry, which combines light from multiple telescopes, allows astronomers to achieve the resolution needed to see stellar disks with surprising clarity. When these high-resolution images were compared with earlier observations, they revealed something remarkable. A significant portion of Betelgeus's visible surface appeared darker than before, as if part of it were obscured or cooled. This observation supported the idea that both surface changes and surrounding dust might be contributing to the dimming effect. The brightness continued to drop. By early 2020, Betelgeuse had reached its lowest recorded brightness in more than a century of careful observation. At its faintest point, it had dimmed to about 1/3 of its normal luminosity. For such a prominent star, this was truly extraordinary. Media attention followed. Headlines began speculating about an imminent supernova, social media filled with dramatic predictions. Some people imagined that an explosion might occur at any moment, creating a celestial light show never seen in modern times. But astronomers responded with characteristic caution. While a supernova was certainly possible in astronomical terms, there was no evidence that one was about to happen in human timescales. The processes that lead to stellar collapse and explosion are incredibly complex. The dimming of a star, even dramatic dimming, does not necessarily mean that catastrophic changes are imminent. Stars like Betelgeuse exist in a constant state of barely controlled chaos. Their outer layers expand and contract, their surfaces bubble and churn, material flows outward in massive stellar winds. What we were witnessing was likely a particularly dramatic example of this ongoing stellar violence. Perhaps an unusually large convection cell had risen to the star's surface, creating a cool, dark region. Perhaps the stellar wind had become temporarily denser, creating more dust and obscuring more light. These explanations, while less sensational than an imminent supernova, are no less fascinating. They remind us that stars are not static objects burning steadily, like cosmic light bulbs. They are dynamic, evolving systems, constantly changing, on timescales that stretch our understanding. The universe itself is not fixed or permanent. Even the stars, which once seemed eternal and unchanging to ancient observers, are part of endless cycles of birth, growth, and death. Every element heavier than hydrogen was forged inside a stellar furnace. Every atom of carbon in your DNA, every molecule of oxygen you breathe, was created when ancient stars lived out their dramatic lives. This perspective transforms our understanding of cosmic events. When we observe a star like Betelgeuse changing dramatically, we're not just watching a distant astronomical phenomenon. We're witnessing the continuation of processes that have shaped the universe for billions of years, and that will continue long after our own sun has burned out. Red supergiant stars exist in a constant state of barely controlled chaos. These massive stellar bodies, nearing the end of their cosmic journey, operate under physical stresses that would obliterate any smaller star. Betelgeuse represents one of our most accessible examples of this phenomenon, a stellar giant that astronomers have watched with fascination for decades. The surface of a red supergiant churns, with convection patterns that dwarf anything we experience on Earth. Imagine cells of superheated gas, each one larger than Earth's entire orbit around the Sun, rising and falling in slow, titanic cycles. These convective movements create dark spots and bright regions across the stellar surface, making the star appear mottled when viewed through our most powerful telescopes. The temperature differences between these regions can span thousands of degrees. Mass loss defines the daily existence of these stellar behemoths. Unlike our Sun, which loses material at a relatively gentle pace, red supergiants hemorrhage matter into space continuously. Solar winds from these stars carry away mass equivalent to Earth's weight every few years. This material doesn't simply vanish. It forms expanding shells of gas and dust that can stretch for light years around the parent star. When this ejected material cools sufficiently, it condenses into microscopic particles we call cosmic dust. These particles, though individually smaller than the wavelength of visible light, can collectively dim starlight in remarkable ways. The dust interacts selectively with different colors of light, scattering blue wavelengths more efficiently than red ones. This selective absorption creates complex dimming patterns that astronomers can decode like fingerprints. Modern astronomical instruments allow us to observe these processes across the entire electromagnetic spectrum. Visible light telescopes show us the obvious changes in brightness, but infrared detectors reveal the warm dust clouds surrounding the star. Radio telescopes can detect molecular emissions from gas clouds drifting far from the stellar surface. Ultraviolet observations highlight the hottest regions where nuclear processes rage most intensely. The timing of stellar events often challenges our human perspective on change. Most stellar evolution occurs over timescales measured in millions of years, far beyond direct human observation. We typically study stellar life cycles by examining different stars at various evolutionary stages, piecing together narratives from cosmic snapshots. Rarely do we witness dramatic changes in individual stars within human lifetimes. Red supergiants operate under different rules than ordinary stars. Their immense size, combined with the violent nuclear processes in their cores, creates an inherently unstable system. Pulsation cycles can cause these stars to expand and contract over periods ranging from months to years. During expansion phases, the stellar surface cools and dims. During contraction, temperatures rise and brightness increases. The convection patterns within red supergiants follow physics that pushes the boundaries of our understanding. The scale of these movements exceeds anything we can replicate in laboratory conditions. Computer models struggle to accurately simulate the turbulent flows, radiation transport, and nuclear reactions occurring simultaneously within these stellar furnaces. Each new observation helps refine our theoretical frameworks. Surface activity on red supergiants can produce eruptions that dwarf solar flares by orders of magnitude. These events can eject material equivalent to several Earth masses in single episodes. The ejected matter travels outward at velocities measured in tens of kilometers per second, eventually forming the circumstellar shells that characterize evolved, massive stars. Constellation patterns provide humanity with some of our most enduring celestial landmarks. These star patterns, learned almost unconsciously, become as familiar as terrestrial geography. When a prominent star in a well-known constellation changes significantly, the alteration strikes observers immediately. Even those with casual interest in astronomy, the human eye, evolved to detect patterns and changes, notices these stellar shifts with surprising sensitivity. Brightness variations in stars have captivated astronomers since ancient times. Early observers noted that certain stars seem to pulse or flicker over periods of days, weeks, or months. These variable stars, as they came to be known, provided some of the first evidence that stars were dynamic rather than fixed points of light. Modern photometry allows us to measure brightness changes with extraordinary precision, detecting variations of less than 1%. Spectroscopic analysis reveals the chemical composition and physical conditions within stellar atmospheres. Different elements absorb light at characteristic wavelengths, creating dark lines in stellar spectra. The strength and shape of these absorption lines tell us about temperature, pressure, chemical abundance, and motion within the stellar atmosphere. For red supergiants, these spectra often show evident substantial mass loss and turbulent motion. The life cycle of massive stars follows a predictable but dramatic arc. Born from collapsing gas clouds, these stellar giants burn through their nuclear fuel at prodigious rates. Their cores progress through successive fusion processes, creating heavier elements from lighter ones. Eventually, the core becomes too massive to support itself against gravity, leading to catastrophic collapse and explosive death. Dust formation in circumstellar environments represents a crucial phase in cosmic recycling. Elements forged within stellar cores through nuclear fusion eventually find their way into the interstellar medium through stellar winds and explosive events. These heavy elements, including carbon, oxygen, and silicon, form the building blocks for planets, and ultimately, life itself. Observational astronomy has evolved tremendously with advances in detector technology and computational power. Arrays of telescopes can now work together, combining their observations to create images with resolution exceeding that of any single instrument. Space-based telescopes avoid atmospheric interference, providing unprecedented clarity for stellar observations. The unpredictability of red supergiants reminds us that even our most sophisticated models cannot perfectly predict stellar behavior. These massive stars exist in states far from equilibrium, making them sensitive to small perturbations that can trigger dramatic changes. Each observation of unusual stellar activity contributes to our broader understanding of stellar physics and evolution. Betelgeuse, one of the brightest stars in our winter sky, sits right there in the constellation of Orion. For most of recorded history, it's been shining at a fairly predictable level. But around 2019, something unusual started happening. The star began to dim noticeably. Now, red supergiant stars like Betelgeuse aren't perfectly steady. They pulsate, they have cooler and warmer regions on their surfaces. Sometimes, these cooler patches which don't radiate as much light can expand or shift around. When that happens, the star appears dimmer from our perspective on Earth. But what happened to Betelgeuse was different. By early 2020, it had reached the faintest level ever recorded, at least since we started keeping reliable measurements over a century ago. At its dimmest point, it was putting out less than half its usual brightness. That's not just a minor fluctuation, that's a real event. Word spread quickly beyond astronomy circles. Newspapers picked up the story, television shows started discussing it. Social media filled with comparison photos showing Orion looking noticeably different. For many people, this was the first time they realized that stars can actually change within a human lifetime. We tend to think of the night sky as this unchanging backdrop, something permanent and eternal. But Betelgeuse reminded everyone that the universe is constantly in motion, constantly evolving, even on timescales we can witness directly. There's something humbling about that, the idea that these cosmic giants we see as fixed points of light are actually dynamic, living entities in their own way. Scientists were quick to point out that this dimming didn't necessarily mean the star was about to explode. The processes that lead to a supernova are incredibly complex, and there wasn't evidence that Betelgeus's core was undergoing the rapid changes that would come before collapse. Still, the possibility, however remote, added an element of anticipation to all the observations. If Betelgeuse were to go supernova, it would be the brightest one visible from Earth in centuries. The last comparable event in our galaxy happened back in 1604, when Johannes Kepler observed what he described as a brilliant new star that shone for months before fading away. Since then, we've seen supernovas in other galaxies, but none close enough to match what Betelgeuse would produce. That historical context made the dimming even more fascinating. Even if it turned out to be unrelated to any imminent explosion, it was still an unprecedented opportunity to study a red supergiant up close. Night after night, telescopes around the world kept watching. One of the challenges with studying Betelgeuse is that it's not a simple, uniform ball of light. Its outer atmosphere is extended and irregular, with massive plumes of gas rising and falling across distances that dwarf our entire solar system. The star's brightness can change not just because of internal processes, but also because of all that material swirling around it. To figure out what was really happening, astronomers used multiple techniques. Spectroscopy gave them information about temperature and motion. Interferometry revealed surface features. Infrared imaging could detect dust clouds. By combining all these different sources of data, scientists started piecing together the puzzle. Gradually, a picture began to emerge. The most likely explanation was that Betelgeuse had experienced a significant outflow of material, possibly triggered by some large convective event or pulsation deep within the star. This material cooled as it expanded outward, forming a cloud of dust that drifted right into our line of sight between the star and Earth. At the same time, the star's surface may have developed a particularly large, cool region, which would further reduce the amount of light reaching us. The combination of these factors produced that dramatic dimming that observers had recorded. It's like the star temporarily pulled a dusty veil across itself. But even with this explanation, there were still puzzling details. The amount of material involved seemed larger than typical mass loss events in similar stars. The timing didn't match perfectly with known pulsation cycles, and the dust cloud appeared to have a complex asymmetric shape rather than forming a simple uniform screen. These uncertainties kept the scientific discussion lively. Papers were written, models were revised, new observations were proposed. Meanwhile, something encouraging started happening. The star began to brighten again. By spring of 2020, measurements showed a gradual increase in luminosity. The change was slow, almost cautious, but unmistakable. Betelgeuse was recovering. For observers who had been following the dimming closely, this was both reassuring and intriguing. Reassuring because it suggested the event was part of the star's natural variability, rather than a sign of imminent collapse. Intriguing because the recovery provided additional data, showing how the star's atmosphere responded as the dust dispersed and surface conditions evolved. Even after the brightness returned to near normal levels, astronomers kept watching Betelgeuse carefully. The event had shown that this star could change in ways that were both rapid and dramatic. Nobody wanted to miss the next episode. Subsequent observations revealed that the star's behavior had indeed shifted slightly. Its pulsation patterns appeared different, with some cycles becoming more pronounced and others less regular. Whether these changes were temporary or part of some longer-term evolution remained an open question. What became clear was that Betelgeuse had entered a new era of scientific attention. More telescopes were watching it than ever before. More data were being collected. More scientists were focusing on understanding the complex processes occurring within and around this enormous star. Events like this great dimming are rare opportunities. Most red supergiants are simply too distant to study in such detail. Betelgeuse, by contrast, is close enough that even subtle changes can be measured with remarkable precision. Each fluctuation in brightness, each shift in spectral lines, Each new image of its mottled surface adds another piece to the puzzle, and that puzzle extends far beyond a single star. Understanding how Betelgeuse behaves helps astronomers refine their models of stellar evolution, particularly the late stages of massive stars. It helps predict how and when such stars lose mass, how their atmospheres change, what conditions might precede a supernova explosion. The dimming of Betelgeuse wasn't just an isolated curiosity. It was a window into processes that shape the chemical evolution of entire galaxies, that influence the formation of new stars and planets. When massive stars like this eventually do explode, they scatter heavy elements throughout space, elements that become the building blocks for future generations of cosmic objects. There's something profound about that connection. The iron in our blood, the calcium in our bones, the oxygen we breathe. All of it was forged inside stars, like Betelgeuse. When we study these stellar giants, we're really studying our own origins, tracing the long chain of cosmic events that made our existence possible. For those who stepped outside on clear nights during that winter of 2019 and 2020, the experience was simpler, but no less meaningful. They saw a familiar star grow faint, then slowly brighten again. They witnessed with their own eyes that the sky is not static, that change is always happening, even in places that seem eternal. For decades before this great dimming, Betelgeuse had been one of the most studied stars in the sky, not because it was behaving strangely, but because it was behaving in ways that made it scientifically useful. A red supergiant close enough to observe in detail is genuinely rare in our galaxy. Astronomers had spent years building models to understand how such stars evolve, how they pulsate, how they lose mass near the ends of their lives. Those models didn't predict every detail, of course. Stars are incredibly complicated objects, with processes occurring across vast ranges of scale and time that challenge our ability to fully comprehend them. Red supergiant stars present some of the most challenging puzzles in modern astrophysics. These massive, aging giants operate on scales that stretch our understanding of stellar behavior. When we peer into their outer layers, we find systems so complex, so turbulent, that even our most sophisticated computer models struggle to capture their full reality. The fundamental nature of these stars involves constant change. Unlike our stable sun, red supergiants exist in a perpetual state of flux. Their outer atmospheres expand and contract in rhythmic cycles. Like the breathing of some cosmic giant, this pulsation drives much of what we observe, creating patterns that astronomers have learned to recognize over decades of careful study. What makes these observations particularly fascinating is how mass loss shapes everything we see. Red supergiants shed material at rates that would seem catastrophic by solar standards. Gas streams away from their surfaces continuously, cooling as it travels outward through the vacuum of space. As temperatures drop, this gas begins to condense, forming tiny grains of dust that scatter starlight in complex ways. The philosophical implications here run deeper than simple mechanics. We're witnessing the universe's recycling program in action. The carbon, oxygen, and heavier elements forged in stellar cores don't remain locked away forever. They drift outward, eventually becoming the raw materials for future generations of stars and planets. In a very real sense, the calcium in our bones, the iron in our blood, once flowed through the outer layers of dying giants much like these. Temperature relationships in stellar atmospheres follow patterns that seem almost intuitive once you understand them. Hotter surfaces shine brighter, cooler ones dim noticeably. This connection allows astronomers to diagnose what's happening inside stars by analyzing the light that reaches us. When brightness changes occur, temperature measurements often reveal whether the star itself has changed, or whether something else is interfering with our view. Spectral analysis provides the key to unlocking these stellar secrets. Every element leaves its fingerprint in starlight, creating dark lines at specific wavelengths. By measuring how these lines shift and change, astronomers can track the movement of gas, monitor temperature variations, and even detect the formation of dust clouds between the star and Earth. The timeframes involved in stellar evolution usually unfold across geological scales. Changes that seem dramatic to us often represent tiny adjustments in cosmic terms. Yet occasionally, Events occur that compress months or years of typical stellar behavior into much shorter periods. These rapid changes offer unique windows into processes that would otherwise remain hidden. Convection patterns in red supergiant atmospheres create a constantly shifting landscape of bright and dark regions. Imagine bubbles of hot gas rising from deep within the star, cooling as they reach the surface, then sinking back down to be reheated. This process creates cellular patterns visible even across interstellar distances, though the cells themselves can be larger than Earth's entire orbit around the Sun. The irregular nature of these convection cells challenges our attempts to predict stellar behavior precisely. While general patterns emerge over time, individual events often surprise researchers with their timing, intensity, or duration. This unpredictability reflects the chaotic nature of fluid dynamics operating under extreme conditions that no earthly laboratory can replicate. High-resolution imaging has revolutionized our ability to study these distant giants. Modern instruments can actually resolve the disks of nearby red supergiants, revealing surface features and asymmetries that were previously invisible. These observations show us that stars are far from perfect spheres. They're dynamic, asymmetric objects shaped by rotation, magnetic fields, and turbulent flows. Gas velocities near stellar surfaces provide clues about the violence of these processes. Material ejected during particularly active periods can reach speeds of hundreds of kilometers per second. These measurements help astronomers understand the mechanisms driving mass loss and the formation of circumstellar material. The concept of stellar personality emerges from long-term observations of variable stars. Each red supergiant develops its own characteristic patterns of brightness variation. Some pulse with clockwork regularity, others show more complex overlapping cycles. This individuality reflects the unique combination of mass, age, rotation, and evolutionary history that defines each star. Recovery patterns after major dimming events often reveal as much about stellar behavior as the events themselves. The way brightness returns to normal levels, whether smoothly or with continued fluctuations, provides insights into the lasting effects of surface activity and mass ejection episodes. Dust formation around evolved stars creates some of the most beautiful and complex structures in astronomy. Rather than forming neat, spherical shells, this material often arranges itself in irregular arcs, clumps, and streams. Turbulent, stellar winds, asymmetric eruptions, and interactions with previously ejected material all contribute to these intricate patterns. The messiness of real stellar systems compared to idealized models reflects a fundamental truth about the universe. Nature rarely conforms to our simplified mathematical descriptions. Instead, it reveals layer upon layer of complexity that keeps astronomers perpetually surprised and humbled. Each unexpected observation opens new questions, driving the endless cycle of discovery that defines scientific progress. Modern computational models excel at describing general stellar behavior, but individual objects consistently reveal nuances that theory hasn't yet captured. This gap between prediction and observation isn't a failure of science, it's an invitation to deeper understanding. Every anomaly, every unexpected measurement pushes our knowledge forward incrementally. The ongoing evolution of red supergiants makes them particularly valuable for studying stellar physics in real time. Unlike main sequence stars that change imperceptibly over human lifetimes, these giants can shift their behavior noticeably within years or even months. This accessibility makes them natural laboratories for testing our understanding of stellar evolution. Long-term monitoring programs track these changes across decades, building databases that reveal patterns invisible in shorter observations. The patience required for such studies reflects astronomy's unique relationship with time. We study objects whose lifetimes span millions of years, using instruments that have existed for mere decades. Betelgeuse had astronomers scratching their heads for months. When this massive red star started dimming dramatically, everyone expected to see the telltale signs of a supernova brewing, but those signs, they just weren't there. No changes in the core structure that would ripple outward, no shifts in neutrino emissions, nothing that suggested this giant was about to explode in spectacular fashion. The universe has this way of keeping us humble. Here we have all these models, all these predictions about how stars should behave, and then nature decides to throw us a curveball. Betelgeuse was dimming, yes, but it wasn't following the script we'd written for dying stars. It was doing something unusual, but not catastrophic, something that made scientists both puzzled and excited at the same time. What they eventually figured out was happening up there tells us something profound about how little we really understand about these cosmic giants. The star had experienced what you might call a massive convective burp. Imagine the largest storm you can think of, then multiply that by a few billion times. Material from deep inside the star got pushed upward, lifted right off the surface in amounts that are almost impossible to comprehend. This expelled material. It cooled down as it drifted away from the star's scorching surface. When gas cools in space, something interesting happens. Atoms start bonding together, forming tiny dust particles. These microscopic grains, they're incredibly effective at blocking visible light. It's like cosmic fog drifting between us and the star, making Betelgeuse appear much dimmer than it actually was. The beauty of this explanation lies in its ordinariness. Red supergiants, like Betelgeuse, they're constantly shedding material. It's part of their nature, like breathing is for us. They puff off their outer layers, creating these magnificent shells of gas and dust that stretch for enormous distances. Astronomers had already seen evidence of this around Betelgeuse, these arcs and structures that spoke of earlier episodes of mass loss. But scale matters in astronomy. What surprised everyone wasn't that dust formed, it was how much dust formed, and how quickly. To create a cloud dense enough to dim such a bright star so dramatically, you need a truly energetic event. Something had to lift a tremendous amount of material off the star's surface in a relatively short time. The clues that solved this mystery came from looking at different types of light. When astronomers measured how much visible light was being blocked versus infrared radiation, they found exactly what they'd expect if dust was the culprit. Dust grains are particularly good at scattering visible light, but they let more infrared radiation pass through. It's like looking at a street lamp through fog. The brightness dims, but you can still feel the heat. Betelgeuse's surface isn't the calm, smooth sphere we might imagine. It's a roiling, turbulent place where enormous convection cells, each one larger than Earth's entire orbit, carry hot material upward while cooler material sinks down. These currents can create incredibly powerful upwellings, regions where gas gets pushed with such force that it breaks free of the star's gravitational grip entirely. What appears to have happened is that one of these upwellings was particularly violent. It created a massive plume of gas that got ejected into space. As this material expanded and cooled, conditions became perfect for dust formation. Molecules could finally bond together without being torn apart by the star's intense heat and radiation. The evidence for this cosmic eruption showed up in the data. Spectroscopic observations revealed gas moving outward from the star at high speeds. High-resolution imaging showed irregular structures in the material surrounding Betelgeuse. The star had essentially sneezed, expelling a cloud of gas that then turned into the dust that dimmed our view. But nature rarely gives us simple answers. The dimming wasn't uniform across the star's surface. One region appeared darker than the rest, suggesting that the dust cloud was concentrated in a particular area rather than spread evenly around the star. This asymmetry told astronomers that the eruption hadn't been a gentle, uniform process. It had been localized, perhaps originating from a specific region where convection was especially intense. The timing raised questions too. The dimming happened relatively quickly, which suggested that the cloud formation and positioning occurred faster than many models predicted. Most theories about stellar winds assume gradual, steady outflows, but Betelgeuse seemed to experience something more episodic, a brief but incredibly powerful event. This challenges our understanding of how massive stars lose mass. We tend to think of stellar evolution as a slow, steady process, but Betelgeuse showed us that these giants can have moments of dramatic activity. They can experience sudden outbursts that eject enormous amounts of material in cosmic eye blinks. There's something almost poetic about dust being the answer to this mystery. These tiny grains, formed from the very atoms that were once deep inside a star, drifting through space and temporarily blocking our view of their birthplace. The carbon, silicon, and other elements that make up this dust, they were forged in the nuclear furnace of Betelgeus itself, then expelled to eventually become part of new worlds, new systems. Each dust grain represents a small piece of stellar alchemy. Inside Betelgeus, lighter elements get fused into heavier ones through processes that release tremendous energy. When material gets expelled from the surface, it carries these newly created elements with it. This dust doesn't just block light, it's also seeding space with the raw materials for future planets and potentially life itself. The fact that we could solve this mystery at all speaks to how far astronomical techniques have advanced. We can now analyze starlight in incredible detail, breaking it down into its component wavelengths to understand not just how bright a star is, but what it's made of and how it's moving. We can create images sharp enough to see structures around distant stars, revealing the complex environments that surround these cosmic giants. But perhaps the most important lesson from Betelgeus's dimming is how much we still don't know. Even with all our technology and theoretical understanding, stars can still surprise us. They operate on timescales and with forces that dwarf human experience. A single convective cell on Betelgeus's surface is larger than our planet's entire orbit around the Sun. The uncertainties that remain continue to drive new research. Scientists want to understand the exact mechanisms that triggered such a powerful eruption. They want to know how often massive stars experience these episodes, and whether they're connected to the eventual supernova process. Each observation of Betelgeuse provides new data about how massive stars live and die. This red supergiant serves as a natural laboratory, allowing us to study processes that we can't replicate on Earth or even fully simulate in our most powerful computers. The physics of convection in a star hundreds of times more massive than our Sun. The interaction between radiation and dust in the harsh environment around a supergiant. The mechanisms that drive mass loss in the final stages of stellar evolution. These are all areas where Betelgeuse provides unique insights. The story of Betelgeuse's great dimming reminds us that the universe still holds surprises. Even objects we've studied for decades can suddenly do something unexpected, forcing us to reconsider our assumptions and expand our understanding. It's a humbling reminder that for all our scientific progress, we're still learning about the cosmos around us. In the end, Betelgeuse returned to its normal brightness, the dust cloud having dispersed or moved out of our line of sight. But the lessons from those months of dimming continue to influence how astronomers think about massive stars. They've been reminded that these giants don't always follow the predictable patterns we expect, that they have their own rhythms and behaviors that can take years or centuries to fully reveal themselves. The next time Betelgeuse does something unexpected, and it probably will, astronomers will be watching with instruments even more sensitive than those that solved the dimming mystery. Each surprise brings new knowledge. Each puzzle reveals another piece of the cosmic story we're all part of. Red supergiants exist in a constant state of restlessness, their outer layers churning with movements so vast they dwarf anything we can truly comprehend. When we look up at these stellar giants, we're witnessing a cosmic dance between forces that have been locked in battle for millions of years. The very nature of these stars defies the steady, predictable existence we might expect from something so massive. Instead, they pulse and breathe like living creatures, expanding and contracting over periods that stretch across months, sometimes years. This breathing motion happens on a scale so enormous that our minds struggle to grasp it fully. Imagine layers of gas, each one larger than our entire solar system, moving outward into space, then falling back toward the star's core. As these layers expand, they cool slightly, like air expanding from a compressed container. When gravity pulls them back inward, they heat up again, compressed by forces beyond imagination. This cosmic breathing creates something remarkable. The star's brightness changes as its surface area and temperature shift. When the outer layers expand, the star appears dimmer. When they contract, it brightens again. These changes follow patterns, slow and deliberate. Like the tides on some impossible ocean, Scientists have spent decades mapping these patterns, discovering that some stars have multiple cycles running simultaneously. One cycle might last 400 days, while another stretches across several years. These overlapping rhythms create a complex symphony of light, brightening and dimming in ways that seem irregular up close, but reveal their deeper order when viewed across longer periods. The physics behind this stellar breathing involves a delicate balance between opposing forces. Deep inside the star, nuclear fusion generates enormous amounts of energy. This energy travels outward through layers of hot gas, but sometimes it becomes trapped in regions where the gas grows more opaque, blocking radiation like clouds blocking sunlight. When energy builds up in these regions, it pushes outward against gravity's inward pull. The outer layers expand under this pressure, but as they do, the gas becomes less dense, more transparent. Energy can escape more easily now, reducing the outward pressure. Gravity reasserts itself, pulling the layers back inward, and the cycle begins anew. This process reveals something profound about the nature of stellar existence. These massive objects, which we might imagine as solid and unchanging, are actually fluid systems in constant motion. They exist in a state of perpetual negotiation between the fundamental forces of the universe. But pulsation alone doesn't explain everything that happens around these stellar giants. The outer layers of red supergiants are also stirred by convection, massive currents of hot gas rising from deep within the star. These convection currents operate on scales that make Earth's weather systems seem insignificant by comparison. Sometimes, when conditions align just right, these convection currents can lift enormous amounts of material completely away from the star's surface. We're talking about masses of gas that could equal thousands of Earths, ejected into space in events that unfold over weeks or months. This ejected material doesn't simply disappear. As it moves away from the star's intense heat, it begins to cool. Molecules form in the cooling gas, and eventually tiny particles of dust condense from these molecules. What started as superheated gas becomes a cloud of solid particles drifting through space. These dust clouds can sometimes position themselves between the star and our line of sight, partially blocking the star's light. From our perspective, the star appears to dim dramatically. The dimming can be so significant that it catches the attention of astronomers around the world, sparking theories about what might be happening to the distant star. High-resolution imaging can sometimes reveal these dust clouds directly, showing faint structures extending outward from the star's surface. Infrared telescopes can detect the warm glow of newly formed dust particles, providing evidence that material has recently been ejected from the star. The process of dust formation around red supergiants offers a glimpse into one of the universe's most important recycling systems. The heavy elements that make up planets, and ultimately life itself, are forged in the nuclear furnaces of massive stars, but those elements remain locked inside the star until events like these massive eruptions scatter them into space. Each time a red supergiant ejects material, it's seeding the surrounding space with the building blocks of future worlds. The dust clouds that form around these stars will eventually disperse, mixing with the thin gas that fills the space between stars. Some of this material will eventually be incorporated into new stars and planetary systems. This cosmic recycling process has been happening for billions of years, gradually enriching the universe with the complex chemistry needed for planets and life. The carbon in our bodies, the oxygen we breathe, the iron in our blood. All of these elements were likely forged in the core of a massive star and scattered into space during events similar to what we observe around red supergiants today. The complexity of these stellar systems challenges our attempts to create simple explanations. Multiple processes often work together, creating effects that are greater than the sum of their parts. A pulsation cycle might coincide with a particularly strong convection current, creating conditions for unusually massive eruptions. Computer models help astronomers understand these interactions, but nature rarely conforms exactly to our simplified descriptions. Each observation reveals new complexities that require more refined theories and deeper understanding. The study of these stellar giants also reminds us of our place in a much larger story. The stars we observe today, are participating in processes that have shaped the universe for billions of years. Their dramatic eruptions and slow pulsations are part of an ongoing cosmic evolution that connects the earliest stars to the possibility of life on distant worlds. When we consider the vast scales involved, both in space and time, it becomes clear that these stellar phenomena operate according to rhythms completely removed from human experience. A single pulsation cycle of a red supergiant might span longer than recorded human history. The dust clouds they create might drift through space for millions of years before being incorporated into new stellar systems. Yet somehow, through patient observation and careful analysis, we've learned to read the stories these stars tell through their changing light. Each brightening and dimming carries information about processes happening hundreds of light years away, in environments so extreme that we can barely imagine them. The ongoing study of red supergiants continues to reveal new aspects of stellar behavior. Some of what we observe may be typical for stars of this type, while other events might be unusual or rare. Distinguishing between normal and exceptional behavior requires long-term observation and comparison with other similar stars. As our instruments become more sensitive and our models more sophisticated, we're likely to discover even more complexity in these stellar systems. Each new observation adds another piece to our understanding of how massive stars live, evolve, and eventually transform into the spectacular explosions we call supernovae. Pulsation alone wasn't telling the complete story. The dimming that scientists observed was much stronger than what they'd expect from a star's normal breathing pattern. This meant that while pulsation definitely played a role, it was more like setting up the stage for something bigger to happen. Think about how a star's atmosphere responds when the outer layers keep expanding and contracting. These motions create shock waves that ripple through all that gas, like throwing a stone into a pond. But instead of water, we're talking about waves moving through material that's hot enough to glow. These shocks squeeze some regions tighter, while they push other areas outward, creating this incredibly complex dance of matter around these massive stars. For Betelgeuse, this whole process might have worked together with convection to create that enormous plume of gas that eventually turned into the dust cloud. It's fascinating how these different mechanisms can combine in ways that amplify each other. Something else caught astronomers' attention after the dimming event. The pulsation patterns themselves seemed to shift slightly. The timing wasn't matching up with previous observations exactly, and some cycles appeared weaker or stronger than they used to be. This raises a really intriguing possibility about what's happening inside the star. As stars age, their internal structure changes, and these changes can alter how they pulsate. If Betelgeuse's pulsations were indeed shifting, it might indicate that the star was moving into a new phase of its evolution. Now, this doesn't necessarily mean a supernova is coming soon, but it could give us clues about how the star's interior is changing over time. Studying these pulsations in detail presents quite a challenge. The outer layers of a red supergiant are incredibly turbulent and irregular. Gas moves around influenced by convection, radiation pressure, the star's rotation, and probably factors we haven't even identified yet. Separating the effects of pulsation from all these other processes requires really careful analysis of data collected over many years. Fortunately, Betelgeuse has been watched for so long that astronomers have extensive records to work with. Measurements of brightness, spectroscopic data, imaging studies, they all come together to provide this detailed picture of how the star's brightness and surface features have changed over time. One of the most interesting discoveries from these studies is that pulsations in red supergiants aren't always perfectly regular. The cycles can vary in length and strength, and new modes of oscillation can appear or disappear as the star evolves. In other words, the star's breathing isn't perfectly rhythmic. Sometimes it takes a deeper breath, sometimes the exhale lasts longer than expected, and over time the whole pattern shifts. This variability makes prediction really difficult. It also means that events like the Great Dimming might not repeat in exactly the same way, even if the same basic mechanisms are at work. There's something almost organic about how these stellar processes unfold, unpredictable despite following physical laws. The sheer scale of these motions is mind-boggling. When Betelgeuse expands during a pulsation cycle, its radius can change by tens of millions of kilometers. The amount of energy involved in moving such vast quantities of gas is enormous. The time scales are long enough that changes appear gradual to us, even though they represent dynamic processes of tremendous power. If you could somehow observe this star from much closer, the surface wouldn't appear calm or steady at all. It would be this landscape of slowly rising and falling regions, with glowing clouds drifting upward and vast currents of gas moving in patterns that take months to complete. From that perspective, the dimming might not seem like a sudden event, but rather part of a continuous process of motion and change. Yet from Earth across hundreds of light years, those slow processes compress into patterns of brightness that can appear quite abrupt. This difference in perspective is really important for understanding how astronomers work. They have to interpret distant observations carefully, translating tiny changes in light into physical processes occurring on scales that are almost beyond imagination. The pulsing star theory provides one piece of the puzzle. It helps explain the timing of the dimming and creates the conditions that allow dust to form, but it doesn't explain everything. The size of that dust cloud, the structure of how the dimming unfolded, and the changes in surface features all suggest that multiple processes were working together. If you could somehow move close enough to Betelgeuse to see it clearly, the first thing you'd notice is that it wouldn't look anything like our Sun. Even through powerful telescopes, the Sun appears relatively uniform, its surface mainly broken by sunspots and occasional flares. Betelgeuse would be completely different. Its outer layers are so extended and so loosely held together that the boundary between surface and atmosphere becomes blurred. Instead of a sharply defined edge, you'd see this vast glowing expanse of gas, uneven in brightness, constantly shifting. It's almost like the difference between looking at a solid ball versus watching a slowly churning cloud. Astronomers call this region the photosphere, the layer from which most visible light escapes. But on a red supergiant, that layer isn't thin or stable like it is on the Sun. It's deep, turbulent, and dynamic, shaped by the movement of enormous currents of gas, rising and sinking over immense distances. To understand why this happens, it helps to think about how energy moves inside a star. Deep in Betelgeuse's core, nuclear reactions continue producing energy that must somehow travel outward to be released as light. In smaller stars like our Sun, much of this energy moves through regions where radiation carries heat outward in a relatively smooth way. But in the outer layers, where the gas becomes cooler and more opaque, energy gets transported mainly by convection. This is the same process that happens in a pot of water on your stove. Water at the bottom heats up, becomes less dense, and rises. As it reaches the surface, it cools, becomes denser, and sinks again. This circulation forms patterns of rising and falling currents that carry heat upward. On the Sun, convection occurs in countless small cells, each roughly the size of a country or continent. These cells give the solar surface a grainy appearance when viewed in high resolution. On Betelgeuse, the situation is dramatically different. Because the star is so large, and its gravity at the surface is so weak, convection operates on an enormous scale. Instead of thousands or millions of small cells, Betelgeuse may have only a handful of giant ones at any given time. Each cell can span a significant fraction of the star's radius, meaning that a single rising plume of hot gas could be larger than Earth's orbit around the Sun. These currents move slowly, taking months or even years to complete a cycle. Hot gas rises from deeper layers, spreads across the surface, cools, and then sinks back down. The process is steady but never perfectly uniform, and the surface brightness reflects these changes. Some regions appear brighter where hot material is rising, others appear darker where cooler gas is sinking. From Earth, these patterns are difficult to see directly, but advances in interferometry have made it possible to actually resolve some of these features. It's remarkable that we can peer across such vast distances and begin to make out the details of processes happening on scales so much larger than anything in our immediate experience. When astronomers peer through their most powerful telescopes at distant stars, They discover surfaces that bubble and churn like massive cauldrons. These aren't the gentle, uniform spheres we might imagine from afar. Instead, they're dynamic landscapes where enormous cells of hot gas rise and fall in patterns that dwarf anything we know on Earth. The surface of a red supergiant reveals itself as a patchwork of bright and dark regions, each one larger than our entire solar system. These aren't permanent features, mind you. They shift and change as vast quantities of material move beneath the star's outer layers. It's convection on a scale that challenges our ability to truly comprehend it, even when we can measure it precisely. Each convective cell carries energy that exceeds the combined output of countless suns like ours. The interactions between neighboring cells create flows so powerful they can literally push material beyond the star's gravitational grip. Sometimes, when conditions align just right, these flows become strong enough to lift gas completely away from the star itself. This process connects directly to one of astronomy's most puzzling recent events. Before a famous red supergiant dimmed dramatically, telescopes detected a large region of its surface growing brighter. This brightening likely indicated hot material welling up from deep within the star. Later, that same region darkened, and observers found a cloud of dust floating nearby in space. It was as if the star had taken a deep breath, then slowly exhaled a vast plume of gas into the cosmos. As that gas expanded and cooled in the cold of space, molecules began forming. Eventually, tiny grains of dust appeared, creating a cloud large enough to partially block the star's light when viewed from Earth. The star had, in essence, dimmed itself with its own exhalation. This connection between surface convection and mass loss represents one of the most active frontiers in stellar physics. Scientists are still piecing together how these giant convective cells interact with the star's natural pulsations, the pressure from its own radiation, and the magnetic fields threading through its atmosphere. Each factor influences how material gets lifted away from the star's surface. The atmosphere of such a star differs dramatically from our Sun's relatively thin envelope. Instead, it extends far beyond the visible surface, creating a vast region where gas moves, expands, and interacts with material being ejected from below. This extended atmosphere isn't static or uniform. It shifts and changes as new material rises from the depths. Within this atmospheric envelope, temperatures and densities vary wildly from place to place. Some regions burn hot enough to emit intense, visible light. Others remain cooler, radiating primarily in infrared wavelengths our eyes can't detect. Dust forms in pockets where conditions happen to be just right, creating an ever-changing tapestry of clouds and filaments that evolve over months and years. From our distant vantage point, all this complexity reduces to a single measurement: the star's brightness. Yet that simple number reflects countless processes occurring across a region larger than the orbit of Jupiter. It's humbling to realize how much information hides within something as seemingly simple as a point of light in our night sky. This boiling, turbulent surface also explains why red supergiants don't vary their brightness in perfectly regular patterns. Stars dominated by simple pulsation can be relatively predictable in their cycles. But convection introduces an element of chaos, much like weather systems on Earth. We can predict general trends in our atmosphere, but the specific details of storms and wind patterns remain difficult to forecast far in advance. The convective cells themselves change size and strength over time. Their interactions produce brightness fluctuations that resist simple mathematical description. It's a reminder that even in the cosmos, where physical laws operate with clockwork precision, complexity emerges from the interplay of simple forces. Computer simulations help astronomers study this convection, though modeling gas motion on such enormous scales pushes even the most powerful computers to their limits. These simulations must simplify some aspects of the physics, but they've confirmed that red supergiant surfaces are indeed dominated by a small number of giant convection cells. They've also shown that boundaries between cells can be unstable, sometimes triggering sudden changes in flow patterns. When such changes occur, they can launch material into the surrounding space. This matches well with observations of red supergiants during their dramatic dimming events. The simulations provide a theoretical framework for understanding what telescopes actually observe. Magnetic fields add another layer of complexity to this picture. While red supergiants have much weaker magnetic fields than our Sun, even modest magnetic forces can influence the motion of charged particles in the star's outer layers. Magnetic activity might help channel gas into plumes or arcs, contributing to the irregular structure of material surrounding these massive stars. The surface temperature of red supergiants, while enormously hot by earthly standards, remains relatively cool compared to other types of stars. Typically around 3,500 degrees Celsius, this temperature explains why these stars appear red, rather than white or blue. This cooler surface also creates favorable conditions for molecules and dust to form in the outer layers. In hotter stars, such materials would be quickly destroyed by intense radiation. But in red supergiants, complex molecules and tiny solid grains can grow and accumulate. Over time, these particles contribute to the dusty environment that plays such an important role in how the star appears and evolves. Infrared telescopes reveal this environment in remarkable detail. Shells and arcs of material extend outward from red supergiants. Evidence of past eruptions and ongoing mass loss. Some of these structures are thousands of years old, slowly drifting away from their parent star and dispersing into the broader interstellar medium. This constant shedding of material means red supergiants gradually lose mass over their lifetimes. Eventually, they shed a significant fraction of their outer layers, enriching the surrounding space with elements forged in their nuclear furnaces. In the shorter term, this process creates a complex and changing environment that influences how the star appears from Earth. During dramatic dimming events, the interplay between convection, pulsation, and dust formation likely reaches an unusually intense combination. Large convective plumes may lift material high into the atmosphere, where it cools and condenses into dust clouds. That dust then drifts into our line of sight, reducing the star's apparent brightness. At the same time, changes in surface brightness caused by the convection itself may amplify the effect, making the dimming appear even more pronounced than dust alone would cause. It's a complex dance of physical processes, each influencing the others in ways that astronomers are still working to fully understand. The ability to witness these processes represents a remarkable achievement in human knowledge. A century ago, astronomers could only guess at the internal workings of stars. Today, they can image the surfaces of distant suns, track the motion of gas and dust, and watch as stars the size of planetary systems slowly reshape themselves over human timescales. Yet, despite this progress, red supergiants continue to surprise us. Their surfaces remain restless, their brightness continues to vary unpredictably, and the exact mechanisms driving their behavior aren't yet fully understood. That uncertainty isn't a failure of science, but rather a reminder of how much wonder still awaits discovery in the cosmos. Perhaps there's something profound in contemplating these stellar giants whose very existence challenges our sense of scale and permanence. They remind us that even the stars, those ancient symbols of constancy, are dynamic, ever-changing entities. Their turbulent surfaces and dramatic outbursts speak to forces and energies that dwarf human experience, yet operate according to the same physical principles we observe in our everyday world. Betelgeuse has become one of the most fascinating subjects in stellar astronomy, mainly because it offers something that was impossible for most of human history. For centuries, every star in the night sky appeared as nothing more than a distant point of light. Even when early telescopes were pointed toward the heavens, this fundamental limitation remained unchanged. Planets could reveal their disks, their moons, their phases, but stars stubbornly remained point-like, their actual surfaces hidden from view. This limitation shaped the entire field of astronomy. For generations, scientists could measure how bright a star appeared, they could determine its color, they could track its motion across the sky, but the actual face of a star remained completely mysterious. It was rather like hearing someone speak through a thick wall, knowing they were there, understanding roughly how loud their voice was, but never being able to see what they actually looked like. Betelgeuse changed everything about this situation, not because it sits particularly close to us in any meaningful sense, 600 light-years represents a distance so vast that human minds struggle to comprehend it in any physical way. But within the scale of our galaxy, this distance counts as relatively nearby. More importantly, Betelgeuse possesses truly enormous dimensions. Its apparent size in our sky, though still incredibly tiny, proves just large enough that modern instruments can begin to resolve actual details across its surface. This breakthrough didn't happen suddenly. It required decades of steady technological progress and the development of entirely new techniques that allowed astronomers to combine light from multiple telescopes simultaneously. This method, known as interferometry, works by capturing starlight at several separate telescopes and then combining those signals with extraordinary precision. When executed correctly, this technique allows astronomers to achieve resolution equivalent to a single telescope whose diameter equals the distance between the individual instruments. In some configurations, this virtual telescope can span hundreds of meters across. Using this approach, astronomers began producing images of Betelgeuse that revealed something truly astonishing. The star was not a uniform, glowing circle as one might expect. Instead, its surface appeared uneven, marked by bright regions and darker patches, shaped by enormous convection currents that had long been predicted by theoretical models, but never directly observed in such remarkable detail. For the first time in astronomical history, scientists were not simply inferring what a distant star might look like based on indirect measurements. They were actually seeing it with their own eyes. The early images remained somewhat blurry, more like artistic impressions than sharp photographs, but even these preliminary glimpses revealed that Betelgeuse was far from smooth or uniform. As imaging techniques continued to improve over time, the pictures became increasingly clear, showing large-scale structures across the star's face. These observations confirmed what theoretical models had suggested for years. The surface of a red supergiant is dominated by a relatively small number of giant convection cells, each one transporting energy from the star's interior to its surface through slow, rolling currents of superheated gas. But the images revealed much more than simple convection patterns. They showed asymmetries in brightness that changed over time, suggesting that the surface remained in constant motion, evolving over periods of months and years. It was as if the star possessed its own form of weather, not weather in the sense of wind and rain that we know on Earth, but large-scale movements of gas and heat that continuously reshaped the visible surface in ways that could now be tracked and studied in real time. The dimming event of 2019 and 2020 suddenly made these imaging techniques even more valuable. Astronomers realized they were witnessing an unprecedented opportunity to watch a dramatic stellar change unfold in real time, not just through measurements of brightness variations, but through direct images of the star's surface and its immediate surroundings. Advanced ground-based telescopes, equipped with sophisticated instruments designed specifically for high-resolution imaging, played crucial roles in documenting this event. Observations taken before and during the dimming period were carefully compared, and the differences proved striking. One entire region of the star appeared significantly darker than it had before. This was not a subtle change, requiring careful analysis to detect. The contrast was strong enough that even processed images, which normally required careful interpretation by experts, clearly showed that part of Betelgeuse's face had dimmed dramatically relative to the rest. Simultaneously, other observations detected material moving away from the star at considerable velocity, consistent with the formation of a substantial dust cloud. Putting these various pieces of evidence together, astronomers began reconstructing what might have actually happened during this remarkable event. A large plume of gas had likely risen from the star's surface, propelled by the intense convection currents below. As this material expanded outward into space, it cooled rapidly, eventually forming dust particles that partially obscured the light coming from behind. Meanwhile, changes in the underlying convection patterns may have produced a large, relatively cool region on the surface itself, contributing to the overall dimming effect. For the first time in the study of stellar evolution, scientists could observe both cause and effect unfolding together in the same stellar system. This represented something entirely new in astronomy. In the past, researchers had observed mass loss and dust formation around distant red supergiants, but they rarely possessed images detailed enough to link these phenomena directly to specific features on individual stars' surfaces. With Betelgeuse, they could actually watch the entire process in action, from initial surface eruption to final dust cloud formation. It was like finally seeing the face behind a voice they had been hearing for centuries. Additional observations came from radio telescope arrays operating at wavelengths longer than visible light, allowing detection of cooler gas and dust that might remain completely invisible to optical instruments. This radio data provided further evidence of large plumes of material extending away from Betelgeuse in complex patterns, confirming that the star was shedding mass through uneven, localized eruptions rather than through smooth, uniform stellar winds. This helped explain why the dimming had appeared so irregular and unpredictable. The dust cloud was not a symmetrical shell surrounding the star uniformly. Instead, it formed a dense, clumpy structure shaped by turbulent processes occurring on the surface below. Observing these details fundamentally changed how astronomers think about red supergiants in general. The traditional picture of steady spherical mass loss began giving way to a more complex understanding, one in which giant plumes and arcs of ejected gas played dominant roles. Betelgeuse was not quietly exhaling material in all directions like a slowly deflating balloon. Instead, it was erupting in slow but powerful bursts, each one reshaping its immediate surroundings. One particularly fascinating aspect of these detailed observations was the realization that the star's surface itself is not really a solid boundary in any conventional sense. The outer layers are so diffuse and extended that the distinction between the star proper and its surrounding atmosphere becomes increasingly blurred. Gas rising from deeper layers can travel enormous distances before finally escaping into interstellar space. This raises profound questions about what we mean when we talk about the size or boundaries of such objects. These stars challenge our everyday understanding of where one thing ends and another begins, existing as gradual transitions rather than sharp divisions between stellar material and empty space. Material flowing up from deep inside a star moves outward in a fascinating dance, gradually thinning out, cooling down as it travels, until it simply becomes part of the space around it. This creates something quite unusual, a star that doesn't really have a clear boundary where it ends and space begins. Betelgeuse exists more like a slow fade into nothingness. The extended atmosphere that results from this makes it incredibly difficult to capture clear images, but at the same time, it offers scientists an enormous amount of information to work with. When astronomers study how light gets absorbed and released at different wavelengths, they can actually map out the temperature and density of gas at various distances from the star itself. This process builds what amounts to a three-dimensional picture of the star's outer regions. During that famous dimming event that captured so much attention, these careful measurements showed that the area around Betelgeuse had developed much more complexity than before, with completely new structures forming in the surrounding gas and dust. Every fresh observation provides another piece of an incredibly complex puzzle. Even with all this remarkable progress, though, creating images of a star's surface remains fundamentally an indirect process. The pictures that interferometry produces get reconstructed from intricate patterns of light, and they require very careful interpretation from experts. These are not photographs in any conventional sense that we might understand. They are representations built entirely from data points and mathematical analysis. Still, the level of detail that astronomers can now achieve would have seemed absolutely impossible just a century ago. It's quite remarkable when you think about it, that human beings standing on this relatively small planet, orbiting what amounts to a fairly ordinary star, have somehow developed the ability to map the surface features of a distant red supergiant located hundreds of light years away from us. What those detailed maps reveal is a star that never stops moving, restless in its behavior, constantly evolving. The surface gets shaped by forces that operate on scales far beyond anything we experience in our daily lives. For scientists who dedicate their careers to studying Betelgeuse, These images represent much more than just pretty pictures. They serve as clues to the internal processes happening deep within the star, evidence of how energy moves through its many layers, how material gets carried outward into the surrounding space. Each bright region tells part of the story. Every dark patch contributes information. Each plume of gas adds another chapter to an ongoing narrative. That story continues to unfold even now. After the Great Dimming event passed, and the star returned to brighter levels, astronomers kept observing Betelgeuse with the same sophisticated instruments, searching for additional changes. Some surface features shifted their positions. New patterns emerged from the chaos. The surrounding clouds of material drifted and evolved in unexpected ways. The star never returned to exactly the same state it had been in before the dimming. This observation teaches us something quite profound about the nature of these cosmic objects. Betelgeuse is not some static thing that occasionally experiences random disturbances. It represents a dynamic system that changes constantly, sometimes slowly and subtly, sometimes more dramatically and noticeably. The dimming event was not an isolated incident that happened once and finished, but rather part of a much larger, ongoing process that has been continuing for thousands of years. What makes Betelgeuse especially fascinating to study is not only that it changes over time, but that it is slowly, gradually coming apart. Not violently in some sudden catastrophic moment, but steadily, methodically, in a process that has likely been happening for tens of thousands of years already. Every single second, enormous quantities of gas drift away from the star, spreading out into the surrounding darkness, eventually becoming part of that vast, incredibly thin medium that exists between stars. In a very real and literal sense, Betelgeuse is losing itself to space, bit by bit. This process is not particularly unusual for red supergiants, but the scale at which it happens becomes difficult to picture or comprehend. Our own sun also loses material continuously. The solar wind carries particles outward in an endless stream, but the amount is relatively tiny compared to the sun's total mass. Betelgeuse, by contrast, sheds material at a rate that is literally millions of times greater than our sun. Over the course of its remaining lifetime, it will lose a significant fraction of its outer layers before its life finally comes to an end. To understand why this dramatic mass loss happens, it helps to think carefully about gravity and how it changes as a star moves through different phases of its life cycle. Gravity is fundamentally what holds any star together as a coherent object. In smaller stars like our Sun, gravity at the surface remains strong enough that gas stays tightly bound to the star. Even when powerful flares and eruptions occur, the material usually falls back down or disperses only very slowly. But in a red supergiant like Betelgeuse, the situation becomes completely different. As a massive star ages and expands dramatically, its outer layers get spread across a much larger volume. The total mass is still there, of course, but it gets distributed across an enormous radius that can be hundreds of times larger than the original star. This means that gravity at the surface becomes incredibly weak, sometimes thousands of times weaker than the gravity we experience at the surface of our Sun. This weak gravity means it takes far less energy to lift material completely away from the star and send it drifting into space. At the same time, the star's luminosity becomes absolutely immense. Radiation pressure, which is the outward push exerted by light itself, becomes strong enough to significantly influence the motion of gas and dust particles. When countless photons leave the surface of Betelgeuse every second, they carry momentum with them. When these photons collide with particles floating in the star's outer layers, they transfer tiny amounts of that momentum to the particles. Individually, each of these pushes is incredibly small, almost negligible. But there are truly countless photons streaming outward every single second of every day. Over time, this cumulative effect can actually help drive material away from the star in a kind of cosmic wind powered by light itself. Convection adds yet another fascinating layer to this complex process. Those giant convection cells that rise and fall across Betelgeuse's surface, like enormous bubbles in a pot of boiling water, can carry gas up to very high altitudes in the star's atmosphere, where gravity becomes even weaker than it already was. Once the material reaches these heights, Radiation pressure and the star's natural pulsation cycles can push it even farther outward, eventually allowing it to escape completely from the star's gravitational influence. This is not a smooth, gentle, steady flow like water from a faucet. The process is irregular and unpredictable, sometimes relatively calm and steady, other times much more energetic and dramatic, constantly shaped by the shifting patterns of convection deep within the star and the complex pulsation cycles that cause the entire star to expand and contract. When astronomers observe Betelgeuse using infrared light, which can penetrate through dust much better than visible light, they can actually see the results of this ongoing mass loss happening in real time. Surrounding the star are vast arcs and shells of gas and dust, like cosmic ripples spreading outward. Some of these structures formed recently, within just the last few years or decades. Others are thousands of years old, ancient by human standards, but mere moments in the life of a star. These expanding structures drift outward at speeds of several kilometers per second, gradually expanding into the interstellar medium that fills the space between stars. Each arc and shell represent us a specific episode of mass loss, a particular moment in the star's history when it expelled more material than usual, perhaps during a period of increased instability or enhanced pulsation. Over thousands and thousands of years, these individual episodes accumulate and build up, creating a layered historical record of the star's outer layers being gradually carried away. If you could somehow watch this process from a safe distance nearby, it would not appear dramatic in the way that explosions or other violent events look dramatic to us. The motion would actually be quite slow, almost serene and peaceful. You would see clouds of softly glowing gas expanding gradually outward, drifting away like morning mist in perfectly still air. But the scale of what you would be witnessing would be absolutely staggering to comprehend. Each individual cloud drifting away might contain enough raw material to eventually form entire planets, perhaps even complete planetary systems, given sufficient time and exactly the right environmental conditions. That material floating away is not empty or meaningless cosmic debris. It contains precious elements that were forged deep inside the star through nuclear fusion processes. Carbon, oxygen, nitrogen, and many others, elements that turn out to be absolutely essential for the formation of complex molecules, solid rocks, liquid oceans, and life itself. Long before Earth even existed as a planet, other massive stars went through exactly these same processes, steadily shedding material that eventually became part of the vast molecular cloud from which our entire solar system later formed. In that profound sense, the slow unraveling that we observe happening to Betelgeuse right now is part of the same ancient cosmic cycle that eventually produced us. From a purely scientific perspective, though, the precise details of how this mass loss process actually works remain not fully understood, even with all our modern technology and sophisticated instruments. One of the major challenges that researchers face is that several different physical processes operate simultaneously and interact with each other in complex ways. Pulsations cause the entire star to expand and contract rhythmically, constantly altering the density and temperature of the outer atmospheric layers. Convection produces localized upwellings of hot gas that can break through the surface and reach high altitudes where escape becomes much easier. Giant stars in their final centuries face a constant battle between the forces trying to tear them apart. Once dust particles begin forming in a star's outer atmosphere, radiation pressure starts working like an invisible hand, pushing these tiny grains away from the surface. The star's own light becomes its enemy, carrying away pieces of itself grain by grain. Magnetic fields weave through this cosmic drama too, though they're much weaker than what we see in smaller stars. These fields still manage to guide charged particles along invisible highways, adding another layer of complexity to an already chaotic process. Every force interacts with every other force, creating a web of cause and effect that challenges our best computer models. When astronomers point their telescopes at these dying giants, they discover something surprising. The material doesn't leave the star's surface evenly, like water flowing from a leaky bucket. Instead, it erupts in massive plumes and arcs. concentrated in specific regions. This tells us that convection plays a starring role in the process. Giant cells of hot gas rise from deep within the star, carrying material upward in powerful localized bursts. Think of it like watching a pot of thick soup boiling. The bubbles don't form everywhere at once. They appear in certain spots, rise to the surface, and then burst. But instead of soup, we're talking about plasma hotter than anything we can imagine. And instead of a small pot, we're dealing with a star hundreds of times wider than our Sun. The famous dimming event that captured headlines was likely one of these dramatic bursts, caught in the act. A massive plume of material rose from the star's surface, cooled as it traveled outward, and formed a cloud of dust particles. This cloud then drifted between us and the star, creating a cosmic eclipse that lasted for months. But that single event was just one moment in a process that's been continuing for thousands of years. These stars build up extended envelopes of material around themselves, like cosmic onions with layer upon layer of expelled gas and dust. Some of this material stays relatively close to the star, still warm enough to glow faintly in infrared light. Other clouds have traveled so far that they've cooled completely and begun to merge with the thin gas that fills the space between stars. When astronomers map these environments using radio and infrared telescopes, they see complex structures that look like shells and filaments stretching across space. It's evidence of repeated episodes of mass loss happening over incredibly long periods. Imagine looking at the rings of a tree to understand its history, except these rings have been twisted, stretched, and scattered by cosmic turbulence and motion. Temperature plays a fascinating role in this stellar death dance. Even though these giant stars shine with incredible brightness, their surface temperatures are actually relatively cool compared to many other stars. This cooler environment allows molecules to form in the outer layers, and these molecules can then stick together to create dust grains much more easily than would be possible on hotter stars. Once dust forms, radiation pressure becomes dramatically more effective at pushing material away from the star. Dust grains interact strongly with light, acting almost like tiny sails that catch the star's radiation and carry gas along with them. This creates a feedback loop that can sustain mass loss for incredibly long periods. Convection lifts the gas, dust forms from cooling material, radiation pressure pushes everything outward, and the cycle continues. Yet, there are aspects of this process that continue to puzzle astronomers. The rate of mass loss doesn't stay constant over time. Sometimes it increases dramatically for short periods, creating those spectacular dimming events. The mechanisms that trigger these episodes aren't always clear. They might involve changes happening deep within the star's core, or they might arise from the chaotic interactions of convection and pulsation happening near the surface. Understanding these variations matters more than you might think. Mass loss plays a crucial role in determining how a massive star will end its life. As these giants shed their outer layers, their internal structure changes in fundamental ways. The core continues evolving, fusing heavier and heavier elements, while the envelope becomes thinner and less tightly bound to the star. Eventually, when the core finally collapses, all that surrounding material will influence how the resulting supernova unfolds. It will shape the shockwave that tears through space and determine the kind of light that reaches telescopes on distant worlds. The slow loss of mass happening now will help determine the nature of that final explosion, whenever it occurs. From our human perspective, it can be difficult to think of stars as temporary things. They seem permanent, almost eternal fixtures in our night sky, but in reality, stars are temporary structures held together by a delicate balance of forces that eventually shifts. These giant stars are simply far enough along in their evolution that we can actually watch that shift happening in real time. Even now, as light from these distant suns reaches Earth night after night, streams of gas are drifting away from their surfaces. These flows are invisible to our eyes, but detectable with sensitive instruments. Each plume carries away a small part of the star, contributing to the vast diffuse clouds that fill our galaxy with the raw materials for future generations of stars and planets. Despite losing enormous amounts of material, these stars remain bright and prominent in our sky, still glowing with the energy of nuclear reactions deep in their cores. That contrast between the immense scale of the star and the gradual nature of its decline makes them compelling subjects for study. It's like watching mountains erode. Except the process happens fast enough that we can actually measure it within a human lifetime. Astronomers continue monitoring these stellar giants carefully, measuring the speed of outflowing gas, analyzing the composition of expelled dust, and watching for brightness changes that reveal new eruptions. Each observation adds to our growing understanding of how massive stars prepare for the final stages of their evolution, slowly and almost imperceptibly transforming themselves. Even after months of observations and countless measurements, parts of stellar behavior still don't fit neatly into our theoretical models. The dust cloud explanation accounts for much of what we see. Pulsations help explain the timing of events. Convection clarifies how material gets lifted from the surface. But when astronomers examine the data closely, there are still details that remain uncertain. Small mismatches between prediction and reality that hint at processes we don't fully understand yet. This situation is familiar to anyone who studies the natural world. The broad outlines of a phenomenon may be clear while the finer details remain elusive. Those details matter because they reveal just how complex the late stages of stellar evolution really are. We're essentially watching the universe recycle itself, one dying star at a time, turning the ashes of ancient suns into the building blocks of future worlds. When we look up at red giant stars, we see points of light that appear steady and unchanging, but that simplicity is deceptive. These massive stellar bodies are incredibly complex, with surfaces that shift and change in ways we're only beginning to understand. The light we observe comes from the entire visible disk of the star, all mixed together into one averaged signal. It's like trying to understand a painting by looking at the average color of all its brushstrokes combined. This averaging effect creates real challenges for astronomers. Even when specific regions of a star undergo dramatic changes, those variations get blended with light from calmer areas. The result is a diluted signal that can mask important details about what's actually happening on the stellar surface. High-resolution imaging helps reveal some of these details, but even our best telescopes can't capture the fine-scale structure needed to map these enormous stellar surfaces completely. The dust formation process around these giant stars presents another fascinating puzzle. Dust grains need very specific conditions to form properly. Temperatures must be cool enough for molecules to stick together when they collide. Particle densities need to be high enough for those collisions to happen regularly. And there must be enough time for tiny particles to grow into larger grains. The problem is that the outer atmospheres of red supergiants are chaotic, turbulent places where radiation and violent motion constantly disrupt these delicate processes. Yet somehow, dust does form around these stars, sometimes very quickly and in enormous quantities. This suggests that certain regions around the star must become particularly favorable for dust formation, perhaps within dense plumes of gas that get lifted upward by massive convection currents. These localized zones might provide the stability needed for dust particles to grow, even while the surrounding environment remains hostile to grain formation. The structure of material around these stars defies our early expectations. Instead of simple, spherical shells expanding outward uniformly, we find complex patterns of arcs, clumps, and twisted filaments stretching into space. These irregular structures tell the story of episodic eruptions that happen asymmetrically, throwing material in some directions while leaving other regions relatively calm. Why these eruptions occur in specific areas of the star, and what triggers them in the first place, remains an open question. Magnetic fields might play a crucial role in shaping these eruptions, but measuring stellar magnetic fields directly is extremely difficult. Even a relatively weak magnetic field could influence the motion of charged particles in the star's atmosphere, guiding the flow of gas and helping to form the plumes we observe. Without precise measurements of magnetic field strength and structure, though this remains largely speculative territory, rotation adds another layer of complexity to the puzzle. These massive stars rotate slowly, but even slow rotation can significantly affect how material moves through the outer layers. Rotation changes convection patterns and influences where mass loss occurs most efficiently. Measuring the exact rotation rate of a star with such an extended, irregular atmosphere presents significant technical challenges, and different research groups have arrived at slightly different results. Deep inside these stars, hidden from direct observation, nuclear fusion processes power the entire system. Theoretical models suggest that heavier elements are being fused in shells around a contracting core, that the details depend on assumptions about how material mixes, how convection operates, and the exact rates of nuclear reactions. Small changes in these parameters can significantly affect predictions about stellar behavior, including pulsation periods and mass loss rates. Some researchers propose that certain red supergiants may be in transitional phases, moving from one stage of core fusion to another. Such transitions could alter energy output and restructure the outer layers, potentially triggering unusual surface activity. But confirming these ideas requires more observational data and more sophisticated theoretical models. Distance measurements introduce yet another source of uncertainty. Even small errors in distance estimates can lead to significant changes in calculated stellar properties like size and luminosity, and those properties directly influence our models of stellar evolution. Recent technological advances have improved the precision of distance measurements, but uncertainties still remain. Historical records add an intriguing dimension to stellar studies. Observations from centuries, and even millennia ago, suggest that some of these stars may have varied in brightness more dramatically than modern observations alone would suggest. Ancient and medieval astronomical records hint at periods when certain stars appeared significantly fainter than usual. If these historical accounts are accurate, then dramatic brightness variations might be part of longer patterns of variability that span centuries or millennia. Interpreting historical records presents its own challenges, though. Brightness descriptions were often qualitative rather than quantitative, and comparisons with other stars depended on observing conditions that aren't always well documented. While these ancient observations are suggestive, they can't provide the definitive answers that modern precision measurements require. The study of red supergiants involves an enormous range of timescales that challenges our understanding. Convection cells develop and evolve over months or years. Pulsation cycles unfold over periods of years. Major mass loss episodes may take decades to develop fully. Changes originating in the stellar core can take thousands of years to influence surface behavior. From our human perspective, we're observing only brief snapshots of processes that unfold over geological timescales. This temporal mismatch makes it difficult to place recent observations in proper context. Was a particular dimming event an isolated incident, or part of a longer trend that spans centuries? Are current pulsation patterns typical for the star, or do they represent a temporary phase in its evolution? These questions may require decades of continuous observation to answer definitively. Connecting observations of individual red supergiants with broader stellar populations presents additional challenges. Each star is unique, shaped by its particular mass, age, composition, and evolutionary history. While general patterns exist across stellar populations, individual differences can be quite significant. What happens on one well-studied star may not exactly match what occurs on other stars of similar mass and age. This uniqueness means astronomers must be cautious about generalizing from single examples, even extensively studied ones. Each star provides valuable data, but building comprehensive models of stellar evolution requires observations of many different systems at various stages of their lives. Despite these uncertainties, progress in stellar astronomy continues at an accelerating pace. New instruments, both ground-based and space-borne, provide more detailed data than previous generations of astronomers could have imagined. Observations across the electromagnetic spectrum, from radio waves to ultraviolet light, reveal different aspects of stellar structure and behavior. Computer models are becoming increasingly sophisticated, incorporating more realistic physics and higher resolution simulations. Each new piece of observational data helps fill gaps in our understanding, but the complete picture remains elusive. Perhaps this incompleteness is part of what makes stellar astronomy so compelling. These distant suns remind us that even with centuries of accumulated knowledge, mysteries still exist in the night sky. Stellar objects behave in ways that challenge our models and push us to develop better instruments and more sophisticated theories. Red supergiants continue their slow, quiet evolution, shedding material into space, pulsating with complex rhythms, gradually reshaping their surfaces over cosmic time. Each night they rise and set, as they have for millennia, but now we observe them with unprecedented attention and awareness. We know that dramatic changes can occur, and we suspect that more surprises may lie ahead. It's difficult to study these massive stars without contemplating the deeper questions their existence raises. These stellar giants are approaching the final stages of their evolutionary journey, not in human timescales, but in the vast sweep of cosmic history. They stand closer to their ultimate fate than to their original birth in stellar nurseries billions of years ago. This perspective adds a profound dimension to every observation and measurement, a reminder that we're witnessing the final chapters of truly extraordinary cosmic stories. Betelgeuse has already burned through its hydrogen fuel, deep in its stellar heart. The nuclear fires that once sustained it for millions of years have moved on to something different. Now the star fuses helium, and heavier elements too, building them up layer by layer. Like an onion made of cosmic fire, each shell burns at different temperatures, creating different elements, and each stage lasts for less time than the one before. It's fascinating how stars age, really. They don't just slowly dim like a candle running out of wax. They go through distinct phases, each one more frantic than the last. Helium burning might last hundreds of thousands of years, which sounds like forever to us, but it's practically a sprint compared to the millions of years hydrogen burning takes. And when stars start fusing silicon, well, that only lasts days. Days, in a life that spans millions of years. But Betelgeuse isn't there yet. Most scientists think it's still working through helium, maybe just starting on some of the heavier stuff. Which means we're watching something like middle age, not the final moments. Though with stars, this massive middle age is still heading towards something spectacular. See, massive stars don't retire quietly. They don't fade away like our sun will, slowly cooling over billions of years. When the core of a massive star can no longer support all the weight pressing down on it, everything happens fast. The core collapses and then explodes outward in what we call a supernova. The energy released is almost incomprehensible. For weeks, maybe months, a single exploding star can outshine billions of other stars combined. The shockwave tears through space, scattering all those heavy elements the star spent its life creating. Carbon, oxygen, iron, all the stuff that planets and life need to exist. What's left behind becomes either a neutron star, which is matter compressed beyond anything we can imagine, or a black hole. That's Betelgeuse's destiny, eventually. But knowing something will happen is very different from knowing when. This is one of those places where human intuition fails us. The final stages of stellar evolution are short, compared to the star's entire life, but they're still long on human timescales. A red supergiant might spend tens of thousands of years in its current phase. Changes that seem dramatic to astronomers, happening over years or decades, are still just tiny pieces of a much longer story. So when Betelgeuse dimmed dramatically, scientists didn't panic and assume a supernova was coming next week. They asked more careful questions. Were there signs that the star's core was approaching collapse? Because the processes that lead to supernovas begin deep inside, far below what we can see. The outer layers might respond to changes happening in the interior, but those responses are indirect, subtle. It's like trying to diagnose what's wrong with a car engine by only looking at the exhaust. You can learn something, but you're not seeing the whole picture. To understand what scientists look for, you have to think about what happens inside these massive stars as they age. Fusion moves in stages, from lighter elements to heavier ones. Each stage happens in shells around the core, like layers in that cosmic onion. And each stage burns faster than the one before it. The pattern accelerates as the star ages. Betelgeuse probably isn't in those final rapid stages yet. It's likely still burning helium, maybe starting to work on carbon and oxygen deeper down, which means the final collapse is still far enough away that we shouldn't expect immediate warning signs. But stars don't always follow the textbook predictions. There have been cases where massive stars showed unusual behavior in the years or decades before exploding. Sudden outbursts, eruptions of material, changes in brightness that hinted at instability. That's why Betelgeus's dimming got so much attention. Not because it proved anything was imminent, but because it raised possibilities. Scientists studied the data carefully. They looked at pulsation periods, temperature changes, the speed of gas flowing away from the surface, the structure of surrounding dust. What they found was interesting, but not alarming. The dimming seemed to come from surface activity and dust formation, not from dramatic changes in the star's internal energy output. The temperature didn't drop drastically. The spectral lines, those fingerprints of light that tell us about a star's composition and behavior, didn't show evidence of rapid structural changes deep inside. In other words, the star was acting unusual, but not in a way that suggested immediate collapse. This distinction matters. The outer layers of red supergiants are naturally unstable. Convection, pulsation, radiation pressure. They create complex environments where large eruptions can happen without any connection to the final stages of core evolution. Storms can be powerful and unpredictable, but they don't necessarily mean the planet itself is about to change fundamentally. Still, the possibility of a future supernova is real, and it's worth thinking about what that would mean, both scientifically and visually. If Betelgeuse exploded, the event would be spectacular from Earth. At peak brightness, it could rival the full moon. It would be visible during the day, a brilliant point of light in broad daylight. At night, it would cast shadows and completely dominate the constellation Orion, but it wouldn't be dangerous. At about 600 light-years away, the energy reaching Earth would be far too weak to cause harm. We'd get a remarkable light show, not a threat. Astronomers would have an extraordinary opportunity to study a nearby supernova in detail, watching the evolution of the explosion from the very beginning, tracking the expansion of debris over years and decades. Yet, for all the fascination around this possibility, the most likely outcome is that Betelgeuse will continue much as it has for thousands of years. Pulsating, shedding material, varying in brightness, without exploding anytime soon. This touches on one of the challenges in astronomy communication. We're drawn to dramatic events, moments of sudden change, but the universe often operates on slower, steadier timescales, where the most important processes unfold gradually. The dimming was dramatic enough to capture attention, but in the context of the star's life, it may have been just another episode in the ongoing mass loss that characterizes red supergiants. Predicting supernovas remains extremely difficult. Even with modern models, astronomers can't look at a star and say precisely how many years remain before it explodes. The internal processes are too complex. Many details depend on factors that can't be measured directly. What scientists can do is estimate ranges, identify evolutionary stages, and watch for signs of rapid change. So far, Betelgeuse hasn't shown those signs. No sudden increases in neutrino emission, no dramatic shifts in spectral features that would indicate rapid core changes, no sustained increase in energy output that might precede collapse. What we see is a star behaving like an aging red supergiant, restless, variable, shedding material, but still stable in its fundamental structure. The uncertainty remains part of the fascination though, because Betelgeuse is close enough and large enough that we can watch it in detail, night after night, year after year. We're not just studying stellar death in theory, we're watching one of the nearest examples unfold in real time. That's rare in astronomy. It's also a reminder that the sky isn't static. The stars we see today won't always be there in the same form. Some will fade, some will explode, some will collapse into things we can barely comprehend. We're witnessing cosmic evolution on a timescale that bridges the gap between human experience and astronomical time. Deep inside stellar cores, temperatures climb to unimaginable heights. We're talking about billions of degrees, where matter behaves in ways that challenge our everyday understanding. At these extreme conditions, atoms get stripped of their electrons completely. What remains is a soup of naked nuclei, colliding with such violence that they overcome their natural tendency to repel each other. This process of nuclear fusion keeps stars burning for millions, sometimes billions of years, but even the most massive stars eventually run out of fuel. When that happens, gravity wins. The core collapses in less than a second, creating pressures so intense that protons and electrons get crushed together into neutrons. The shock wave from this collapse races outward through the star's layers. Hours pass, sometimes longer, before this wave reaches the surface. Only then does the star suddenly brighten, marking the beginning of what we call a supernova. It's remarkable how something so catastrophic can take time to reveal itself to distant observers. From our perspective on Earth, we would witness this transformation as a gradual brightening over several days. Each night, the star would appear more luminous than before. Amateur astronomers, with their careful measurements and patient observations, would likely be the first to notice something unusual happening. There's something deeply humbling about imagining such an event. Picture yourself stepping outside on a clear evening, expecting to see the familiar pattern of Orion, the three bright stars of the belt, exactly where they've always been. But tonight, something has changed. One star burns with an intensity that makes all the others seem dim by comparison. Within a week or two, this stellar explosion might rival the brightness of the full moon. Unlike the moon, though, it would still appear as a single point of light. In dark locations, far from city lights, it might even cast faint shadows on the ground. The entire constellation would be transformed, its ancient balance completely altered by this single, brilliant newcomer. Throughout history, humans have recorded such events with a mixture of wonder and concern. Chinese astronomers in the year 1054 documented a star so bright it remained visible in daylight for weeks. That explosion created what we now call the Crab Nebula, an expanding cloud of gas that telescopes can still observe nearly 1,000 years later. The light from such an explosion doesn't maintain its peak brightness indefinitely. After reaching maximum luminosity, it begins a slow, steady decline. Over weeks and months, the supernova gradually fades, though it remains easily visible to the naked eye for an extended period. During this time, the color might shift slightly as the expanding gas cools and changes. What fascinates scientists most are the invisible messengers that arise before the light itself. Neutrinos, those ghostly particles that barely interact with matter, would reach Earth hours before the explosion becomes visible. Deep underground detectors might record a sudden burst of these particles, providing the first hint that something extraordinary has occurred. Gravitational waves, ripples in the fabric of space itself, might also carry information about the collapse. These signals would offer insights into the internal processes of the explosion, details that light alone cannot reveal. It's as if the universe provides multiple channels for telling the same incredible story. For most people, though, the experience would be purely visual, a brilliant new star appearing in the sky, bright enough to see even during twilight hours. Slowly, night after night, it would fade from view. There's something poetic about watching such a distant event unfold, knowing that what you're seeing is the aftermath of one of nature's most powerful phenomena. Years would pass before telescopes could reveal the expanding shell of gas left behind. What started as a point of light would gradually become a glowing cloud, spreading outward at tremendous speeds. At the center of this nebula, something remarkable might remain. Either a neutron star, so dense that a teaspoon of its material would weigh billions of tons, or perhaps a black hole, invisible except for its gravitational influence. Despite the immense energies involved, such an event would pose no threat to Earth. The vast distances between stars serve as a natural protection, ensuring that even the most violent stellar explosions remain spectacular but harmless. There might be subtle effects detectable by sensitive instruments, slight increases in cosmic radiation, perhaps minor changes in the upper atmosphere, but nothing that would affect daily life. This distance offers a kind of cosmic perspective on our place in the universe. We can witness events of extraordinary power while remaining safely removed from their immediate effects. The night sky becomes a theater where the most dramatic stories unfold, visible to anyone who takes the time to look up and wonder about what they're seeing. The challenge for astronomers lies in predicting exactly how such events might unfold. The brightness of stellar explosions depends on numerous factors, including the star's mass, its composition, and the precise mechanism of collapse. Each supernova tells a slightly different story, shaped by the unique history of the star that created it. These stellar deaths also serve as cosmic recycling centers. The heavy elements forged in stellar cores, everything from carbon to iron, get scattered into space during these explosions. Eventually, this enriched material becomes part of new star systems, new planets, and potentially new forms of life. In a very real sense, we are made from the ashes of ancient supernovae, connected to these distant explosions in the most fundamental way possible. When a massive star like Betelgeuse finally reaches its explosive end, the sheer scale of energy release defies comprehension. In just seconds, that dying giant would unleash the same amount of energy our Sun will produce across its entire 10 billion-year lifetime. It's a reminder that the universe operates on levels of power and violence far beyond anything we encounter in our daily existence. The explosion wouldn't create a simple, steady light show either. Betelgeuse has already been shedding material for millennia, creating a complex bubble of gas and dust around itself. When the supernova shockwave hits this surrounding material, it produces secondary bursts of brightness. The light curve becomes irregular, with peaks and valleys, moments where the glow suddenly intensifies again before continuing its fade. From our perspective on Earth, we'd see a single brilliant point of light. But in reality, that explosion would create an expanding sphere of glowing plasma, thousands of times larger than the original star. Within weeks, this bubble of superheated gas would grow to dimensions that dwarf our solar system. The temperatures inside would reach billions of degrees, hot enough to forge the heaviest elements in the universe. Such an event would become a generational memory. People would remember exactly where they were when Betelgeuse exploded, the same way we remember eclipses or the appearance of bright comets. It would shine during daylight hours, for weeks, visible even against the blue sky. At night, it would cast shadows, a second moon hanging in Orion's shoulder. But Betelgeuse hasn't exploded yet. The great dimming that captured so much attention turned out to be something far more mundane, though no less fascinating. It was a surface event, dramatic but temporary, a massive dust cloud that temporarily blocked our view of the star's light. When the dimming ended, and Betelgeuse slowly brightened again, Orion regained its familiar appearance. To casual observers, everything seemed normal. Astronomers knew better though. The star had quieted down, but it hadn't returned to its previous behavior. The brightness cycles that had once followed relatively predictable patterns now seemed different. Some variations were stronger than expected, others weaker. Some appeared out of phase with previous observations. Betelgeuse had changed its rhythm. This matters because variable stars like Betelgeuse reveal their secrets through their patterns of brightness. Modern instruments can measure these changes with extraordinary precision, tracking even tiny variations over time. Before the dimming, Betelgeuse's light curve showed regulatable cycles, irregular but familiar. After the dimming, those patterns looked different. The amplitude of variations changed, meaning how much the brightness rose and fell during each cycle. Some pulsations became more pronounced while others seemed dampened. This suggested that the star's outer layers had been altered by the events that created the dust cloud. When Betelgeuse expelled that massive plume of gas, it lost material from its atmosphere. Even though the amount was small compared to the star's total mass, it could still affect how energy moves through the outer layers. Stars aren't rigid objects. Their atmospheres respond to changes in pressure, temperature, and density, adjusting gradually until reaching a new equilibrium. During that adjustment period, pulsation patterns can shift for years or even decades. The dust cloud itself didn't simply vanish either. It expanded and dispersed, becoming part of the complex environment surrounding the star. Some of that material might still be influencing how light escapes from the surface. The giant convection cells that shape Betelgeus's surface aren't fixed in place either. They evolve, merge, and break apart over time. After a major event, like the one that produced the dimming, these convection patterns may reorganize completely. New regions of rising and sinking gas form, creating different distributions of bright and dark areas across the surface. This reorganization contributes to brightness changes that don't follow the old cycles. Temperature variations across the star's surface have also changed slightly since the dimming. The differences are small, but they hint that the outer layers are still settling into a new configuration. All of this points to a star that experienced a significant disturbance and is now gradually adjusting to its new state. There's something almost philosophical about watching these cosmic giants slowly evolve. Stars in the red supergiant phase aren't static entities. Their cores continue changing as heavier elements undergo fusion. These internal changes influence the outer layers in ways that take time to become visible. It's possible that Betelgeuse was already undergoing gradual transitions before the dimming occurred, and the event simply made those changes more noticeable. The fluctuations observed in recent years don't match previously identified pulsation periods. Some variations appear at unexpected times, or with durations that differ from known cycles. This doesn't mean the star is becoming chaotic or dramatically unstable. It simply means that the overlapping rhythms that once defined its variability have shifted, perhaps because the star's internal structure continues its slow evolution toward an inevitable end. In the grand scheme of stellar evolution, these changes represent just moments in a process that spans millions of years. Yet for us, watching from our tiny world, they offer glimpses into the profound forces that shape the universe. Every brightness variation tells a story about nuclear fusion, convection, mass loss, and the complex physics governing these stellar behemoths. We're witnessing the slow-motion death throes of a giant, played out across timescales that dwarf human civilization itself. When massive stars reach their final chapters, they begin to reveal secrets about processes that have puzzled scientists for generations. The way these giant suns lose mass isn't the smooth, predictable flow that astronomers once imagined. Instead, it's messy, clumpy, and surprisingly chaotic. Picture material getting ejected from a star's surface in irregular bursts. These aren't gentle breezes of gas drifting away uniformly. They're more like massive plumes shooting out from specific regions, carrying tremendous amounts of stellar material into the void. This creates shells and arcs of gas that twist through space, each one telling a story about what happened deep inside the star. The complexity doesn't stop there. When large amounts of material get thrown out, the density and temperature of the surrounding gas change dramatically. These shifts affect how energy escapes from the star itself. It's like throwing a blanket over a campfire, except the blanket is made of stellar debris, and the fire is a nuclear furnace millions of miles across. Dust plays a fascinating role in this cosmic drama. As particles form and get destroyed in the space around these dying giants, they absorb radiation and re-emit it at different wavelengths. This influences the temperature of nearby gas, creating feedback loops that can take years or even decades to settle down. The dust becomes both a product of the star's instability and a cause of further changes. What makes this even more intriguing is how all these processes interact. Convection, the massive churning of gas that moves heat from a star's interior to its surface, isn't just a background process anymore. In these red supergiants, convection becomes one of the dominant forces shaping everything we observe. Think of enormous cells of hot gas, rising and falling across the star's surface like bubbles in boiling water. Except each bubble is larger than our entire solar system. These create huge temperature differences across the star's face. A region that glows brightly one year might become noticeably dimmer the next, not because the whole star has cooled, but because the flow patterns underneath have shifted. This teaches us something profound about stellar instability. For a long time, scientists assumed that the dramatic changes in massive stars began deep in their cores, but observations now show that much of the action actually starts at the surface, in these vast convective patterns that are constantly reshaping themselves. Pulsations add another layer to this complexity. Stars naturally oscillate, growing larger and smaller in predictable rhythms driven by the physics of their interiors. But in these evolved giants, those pulsations don't happen in isolation. They interact with convection and mass loss in ways that make them far less regular than anyone expected. Instead of neat, repeating cycles, brightness variations can overlap, amplify each other, or dampen unexpectedly. A pulsation that might have been modest under normal conditions can become dramatically amplified when it coincides with a large convective plume or a change in the star's outer atmosphere. This interplay between different forms of variability has become one of the most important areas of modern stellar research. Scientists now understand that instability is rarely the result of a single cause. It's more like a symphony where multiple instruments are playing, sometimes in harmony, sometimes creating discord, but always producing something more complex than any individual component. Computer simulations struggle to capture all these details accurately. Modeling the interaction between convection, pulsation, and mass loss over long periods remains one of the most challenging problems in astrophysics. The calculations are so complex that even our most powerful computers can only approximate what's really happening. This is why continued observation becomes crucial. Each new measurement helps refine the theoretical models and test our understanding. Space-based telescopes contribute data at wavelengths that can't be observed from Earth's surface, revealing the structure of gas and dust surrounding these massive stars. All this information builds a picture of stars that are constantly evolving, changing in ways that are sometimes subtle and sometimes dramatic. But there's a psychological dimension to how we perceive these changes that's worth considering. When dramatic stellar events capture public attention, people often expect the excitement to continue indefinitely. When things return to apparent normalcy, interest fades. Headlines disappear. The conversation moves on to other topics. But for astronomers, these quiet periods can be just as revealing as the dramatic ones. What we perceive as a return to stability might simply be a quieter interval in a much longer sequence of changes. If you could watch a massive star every night for centuries, you might see periods of apparent steadiness alternating with episodes of more dramatic variation. Over even longer timescales, those patterns might shift again and again, reflecting the slow evolution of the star's interior and atmosphere. This highlights an important perspective in astronomy. What appears extraordinary to us observing for only a few decades might be quite ordinary on cosmic timescales. A dramatic dimming that captures worldwide attention might be just one phase in an ongoing process that spans millennia. Yet even these supposedly ordinary processes can teach us extraordinary things. By studying how massive stars behave during their restless final phases, scientists learn about stellar evolution, atmospheric elements that will eventually enrich the cosmos. These lessons apply not just to individual stars, but to countless others scattered across the galaxy. Stars that will one day explode as supernovae, scattering the elements necessary for planets and life throughout the universe. The instruments continue revealing subtle variations, small deviations from past patterns, signs that these massive stars are still adjusting, still changing, still offering new clues to those who watch carefully. What makes nearby examples so valuable isn't just their brightness or proximity, but the fact that we can observe changes while they're still unfolding. Many massive stars that reach the ends of their lives do so in distant galaxies. Their stories get compressed into brief flashes of light. Astronomers see the explosion, study the debris, then work backward, trying to reconstruct what must have happened in the years or centuries before the final moment. With nearby examples, the situation is completely different. Here are massive stars close enough, that we can watch them year after year, measuring their brightness, imaging their surfaces, tracking the gas and dust drifting away from them. Instead of studying the aftermath, we're witnessing the slow, restless behavior of stars that haven't yet reached their final moments, but are clearly no longer in the calm middle phases of their lives. This makes them natural laboratories, quietly demonstrating how unstable massive stars behave as they approach the end of their evolution. One of the first lessons they offer is that stellar instability isn't a single process, but a combination of many processes acting together. For decades, it was tempting to think of late-stage stellar evolution in relatively simple terms. The core evolves, outer layers expand, mass gets lost through stellar winds, and eventually the star explodes. That basic outline remains correct, but the details prove far more complicated than anyone imagined. The giant convective cells rising and falling across these stars' surfaces create temperature differences that can drive eruptions of gas and influence where dust forms in the surrounding space. These convective patterns aren't steady or symmetrical. They change over time, sometimes slowly, sometimes more abruptly. This has helped astronomers understand that instability in massive stars often begins at the surface, not only deep in the core where nuclear reactions are winding down. It's a reminder that even in our most advanced models of stellar physics, there are still surprises waiting to be discovered. The observations have also reshaped our understanding of how these stars lose mass. Earlier models assumed red supergiants lose material in relatively smooth spherical winds, with gas flowing outward more or less evenly in all directions. Reality proves much more interesting. The outflow of gas is often irregular and episodic, with large plumes emerging from particular regions on the surface. These plumes carry significant amounts of material into space, creating the arcs and shells of debris that eventually become part of the interstellar medium, the raw material for future generations of stars and planets. As material drifts away from a dying star, it doesn't travel in neat, orderly patterns. Instead, these ejected clouds bump into older material that was thrown off years before. This creates something fascinating, a complex, layered structure around the star, almost like geological strata in space. Each layer tells a story of a different time, a different episode of stellar instability. This chaotic mass loss process matters more than you might think. When a massive star finally reaches its explosive end, the way that supernova shockwave travels depends entirely on what's already out there. The gas, the dust, the irregular clumps of material, they all influence how bright the explosion will be, how the energy spreads, what kind of nebula forms afterward. It's a bit like how the landscape shapes a wildfire. The same spark behaves completely differently depending on whether it encounters dry grass, dense forest, or rocky terrain. Stars work similarly, and by watching how material flows away from red supergiants now, astronomers can better understand the spectacular explosions they'll observe in distant galaxies later. Time moves differently when you're dealing with stellar death. One of the most important lessons these unstable giants teach us is that instability doesn't mean immediate collapse. A star can spend thousands of years in this restless state, throwing off material, changing its surface patterns, fluctuating in brightness. The outer layers might be in complete turmoil while the core continues its slow, inevitable evolution towards something more dramatic. This corrects a common misunderstanding. When people hear that a star is unstable, it's natural to imagine it might explode tomorrow. That stellar instability is often just a normal part of aging, like grey hair or creaking joints. It's a sign that the delicate balance between crushing gravity and outward pressure is becoming more precarious, but not necessarily that the end is imminent. The famous red supergiant in Orion demonstrates this perfectly. Despite dramatic brightness changes and visible surface restructuring, there's no evidence it's about to become a supernova. What we're witnessing is the long, gradual approach to that final event, not the event itself. It's like watching someone slowly climb a mountain, knowing they'll eventually reach the summit, but understanding that each step is part of a much longer journey. These dying stars are also cosmic dust factories, and dust might sound mundane, but it's actually profound stuff. Dust grains provide the surfaces where complex molecules can form, including organic compounds that might eventually become parts of living systems. Dust helps cool vast interstellar clouds, allowing them to collapse under their own gravity and birth new stars. Dust becomes the seed material for planets. When astronomers watch dust forming in the plumes and shells around red supergiants, they're essentially observing the creation of raw materials for future solar systems. During particularly dramatic dimming events, scientists get rare opportunities to watch this process almost in real time, linking surface activity directly to the birth of new cosmic material. There's something humbling about how these observations challenge our models. For decades, researchers have built sophisticated computer simulations of stellar evolution, incorporating complex physics of nuclear reactions, radiation transport, fluid dynamics. These models are powerful tools, but they must constantly be tested against what actually happens in space. Real stars often behave in ways that surprise even experts. The scale of brightness changes, the structure of dust clouds, the patterns of stellar pulsation, all reveal complexities that weren't fully captured in earlier theories. This doesn't mean the science was wrong. It means it was incomplete. Real nature is messier, more intricate, more interesting than our best theoretical frameworks can fully predict. Science advances through exactly these kinds of challenges. Each unexpected observation forces researchers to refine their ideas, look more carefully, ask better questions. It's like solving a puzzle where the pieces keep changing shape, requiring constant adaptation and creativity. Modern astronomy itself has been transformed by how we study these stellar giants. In the past, detailed stellar observations required large telescopes and specialized equipment, often limiting research to small groups of scientists. Today, networks of telescopes around the world, both professional and amateur, contribute data continuously. Space-based observatories add measurements at wavelengths invisible from Earth's surface. Computer algorithms analyze and interpret information in ways that would have been impossible just a generation ago. The study of unstable red supergiants has become a truly collaborative effort on a global scale, demonstrating how modern science works best, not as isolated observations, but as coordinated campaigns involving many instruments, many researchers, many perspectives working together toward common understanding. Perhaps the quieter lesson is about impermanence itself. These observations remind us that the universe is not static. Even stars we think of as permanent fixtures are changing, evolving, shedding material, moving slowly toward their eventual ends. The night sky feels timeless because human lifespans are brief compared to stellar lifetimes, but the stars themselves are part of continuous cycles of birth, change, death, rebirth. For many people, watching a bright, familiar star change noticeably within a single observing season has made stellar evolution more tangible. That experience brings the reality of cosmic change a little closer to everyday awareness. We're witnessing processes that usually unfold over timescales so vast, they're almost incomprehensible, compressed into changes we can actually observe. As observations continue, these stellar laboratories will keep teaching, not necessarily through dramatic events every year, but through steady accumulation of data, slow unfolding of processes that take decades to reveal themselves fully. Astronomers will keep measuring brightness variations, mapping surface changes, tracking gas and dust drifting away into darkness. Each measurement adds another piece to the cosmic puzzle, helping answer questions not only about individual stars, but about the countless other unstable giants scattered throughout our galaxy. Because ultimately these nearby examples aren't unique in their nature, only in their proximity. There are thousands of red supergiants in the Milky Way, each undergoing similar processes, each shedding material, each evolving toward the same inevitable fate. What makes certain stars special is that we can watch them closely enough to learn from them. Those lessons are changing how astronomers think about late-stage stellar evolution, revealing that instability isn't a brief prelude to collapse, but a long, complex phase filled with subtle changes and occasional dramatic episodes. This phase shapes not only the fate of individual stars, but also their surrounding environment, enriching space with elements that will eventually become part of new stars, new planets, perhaps even new forms of life. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in stellar cores and distributed through space by exactly these processes we're watching unfold. At first glance, the behavior of distant red supergiants might seem like astronomical curiosities, interesting but removed from daily life on Earth. But the deeper truth is quieter and more profound. The reason scientists care so intensely about these stellar death throes is that this behavior touches fundamental questions about how the universe works, how stars shape galaxies, how the basic conditions for life itself emerge from cosmic cycles of creation and destruction. Every single atom in your body, except for hydrogen, was born inside a star. The carbon that forms your DNA, the oxygen you breathe, the iron flowing through your blood, all of it came from stellar furnaces. These elements didn't exist when the universe was young. They had to be created, forged in the nuclear hearts of stars, then scattered across space when those stars died. This process has been happening for billions of years. Stars live, they burn, they explode, and they seed the cosmos with the ingredients for new worlds. The cloud of gas and dust that eventually became our solar system was enriched by countless generations of dead stars. In a very real sense, we are made of stardust. Red supergiant stars play a crucial role in this cosmic recycling program. These are massive stars, much bigger than our sun, and they live fast and die young. They evolve quickly, burning through their fuel in just a few million years, instead of the billions our sun will take. When they die, they do so spectacularly, in supernova explosions that can outshine entire galaxies for weeks. But before they explode, these red supergiants go through dramatic changes. Their outer layers swell up, becoming so large they could engulf the inner planets of our solar system. They pulsate and vary in brightness. They lose mass, casting off their outer atmospheres into space. All of this creates a complex environment around the star, full of gas and dust and magnetic fields. Most red supergiants are too far away for us to study these processes in detail. We can measure their brightness, analyze their light with telescopes, but we can't see what's actually happening on their surfaces. That's what makes nearby red supergiants so valuable to astronomers. They become natural laboratories where we can watch stellar evolution unfold in real time. When astronomers study these massive stars, they're not just satisfying curiosity about distant objects. They're trying to understand the chain of events that made our existence possible. The chemical evolution of galaxies depends on how these stars live and die. The way they lose mass, the elements they create and distribute, the shock waves they send through interstellar space, all of this influences how the next generation of stars and planets will form. The details matter more than you might expect. The structure of the gas cloud around a red supergiant before it explodes actually affects how bright the supernova will be, and astronomers use supernova brightness to measure distances across the universe. So understanding how these stars shed their outer layers connects to some of the biggest questions in cosmology, including how fast the universe is expanding. Convection is another piece of this puzzle that has wide-ranging importance. Inside massive stars, hot gas rises from the core, while cooler gas sinks down, creating enormous convection cells. This process transports energy from the nuclear furnace at the star's center to its surface. But convection in red supergiants happens on scales that dwarf anything we see on Earth. Individual convection cells can be larger than our entire planet. This same physical process occurs in many different types of stars, including our Sun. By studying convection in red supergiants, where it's easier to observe because of the star's enormous size, astronomers can refine their understanding of energy transport in stellar interiors generally. This affects predictions about how long stars will live, how bright they'll be, and how they'll evolve over time. Dust formation around these stars is another area where local observations have global implications. The tiny grains of dust that form in the cool outer atmospheres of red supergiants eventually drift into interstellar space. This dust affects how light travels through galaxies. It provides the raw material for planet formation around new stars, It influences the chemistry of the interstellar medium and plays a role in the birth of the next generation of stellar systems. When we can observe dust forming around a nearby red supergiant in real time, we're watching one of the fundamental processes that shapes the structure and evolution of galaxies. Each tiny grain represents a step in a long journey from stellar death to planetary birth. There's something profound about being able to witness these changes as they happen. Most of astronomy involves studying light that has traveled for millions or billions of years to reach us. We're seeing distant galaxies as they were in the ancient past. We observe supernovas long after the explosion has finished. Much of our understanding of the universe comes from interpreting these delayed signals from cosmic history. But with nearby variable stars, we can watch change unfolding on human timescales. We can see brightness variations from month to month. We can compare images taken a year apart and notice real differences. We can follow the evolution of dust clouds as they expand and disperse around the star. This immediacy is rare in astronomy and incredibly valuable for testing theoretical models against ongoing observations. It also gives the public a chance to experience astronomy as a living science, rather than a collection of finished facts. When people realize that stars are not fixed points of light, but dynamic objects that change over time, it transforms how they think about the night sky. The heavens become not just a beautiful backdrop, but a story in progress, full of drama and transformation. There's a deeper philosophical dimension to all of this that doesn't require complicated concepts to appreciate. These stellar changes remind us that transformation is universal. Even objects that seem permanent, stars that have shone steadily for millions of years, are subject to the same fundamental processes of growth, change and eventual decline that shape everything in nature. This isn't cause for melancholy. It's simply part of the rhythm of existence, the cycle through which matter is continually recycled and reorganized into new forms. The elements in your body were once part of the ancient stars that died before our solar system was born. Someday, far in the future, the material of our planet will return to space and become part of new stars and worlds. This perspective can be oddly comforting. When you consider the enormous scales involved, the vast distances across space, the billions of years of cosmic time, everyday concerns begin to feel different, not unimportant, but placed in a broader context. Astronomy has this gentle way of reminding us that we live on a small world in an immense universe, and that the forces shaping that universe operate on timescales far beyond human experience. Yet we're not separate from these cosmic processes, we're part of them. The same physics that governs the life cycle of stars governs the chemistry of our bodies. The same elements forged in stellar cores make up our planet and everything on it. We're intimately connected to the stars, not just poetically, but literally, through the shared history of matter itself. This connection becomes more than abstract knowledge when we can observe stellar evolution happening in real time. Watching a red supergiant vary in brightness is like watching the slow rhythm of cosmic breathing, the rise and fall of processes that have been shaping the universe since the first stars formed. Each observation reveals new subtleties, new complexities that challenge our understanding. Despite centuries of study, stars continue to surprise astronomers. New instruments reveal previously invisible details. Fresh observations sometimes contradict existing theories. The universe remains more intricate and more mysterious than we often expect. That's one reason scientists are drawn to these stellar mysteries. Each puzzle isn't just a problem to be solved, but a doorway to deeper understanding. Every answer uncovers new questions, and questions are what drive science forward. The dimming and brightening of red supergiants connects quietly, but directly to some of the most fundamental questions about how the universe works. From the smallest scales of dust grain formation to the largest scales of cosmic expansion, the physical laws that shape stellar cores operate inside our own bodies too. Every atom that makes up your bones, your blood, your breath, follows the same fundamental rules that govern distant suns. It's a connection that spans unimaginable distances, linking us to processes we'll never witness directly. The elements flowing through your veins right now were forged in ancient stellar furnaces, much like the one burning inside Betelgeus today. When you think about it, We're essentially made of star stuff that's been recycling through the cosmos for billions of years. The calcium strengthening your teeth, the iron carrying oxygen through your bloodstream, the carbon forming your DNA. All of these came from stars that died long before our solar system even existed. What's happening inside Betelgeuse now is part of that same endless cycle, creating new elements that will eventually drift into space, cool into dust, and perhaps one day become part of new worlds. Science moves forward through this kind of patient observation, one measurement at a time. Astronomers continue studying Betelgeuse because each observation adds another piece to a cosmic puzzle that's been millions of years in the making. The data accumulates slowly, models get refined, old questions find answers while new mysteries emerge. This gradual process of discovery reflects something deeper about how knowledge grows, how understanding develops through careful attention rather than sudden revelation. There's something quietly remarkable about our ability to understand any of this at all. A species that evolved on one small planet has somehow developed instruments capable of imaging the surface of distant stars. We can measure gas currents drifting through space, reconstruct the life cycles of objects that live for millions of years. When you consider the odds against such understanding ever developing, it becomes almost miraculous that we can peer into the workings of stellar giants. If you step outside tonight and look toward Orion, you'll see Betelgeuse much as people have seen it for thousands of years, a steady reddish glow marking the hunter's shoulder. At first glance, nothing suggests turmoil or change. It appears calm, patient, almost permanent in the way bright stars often seem. But knowing its story changes everything about how you perceive that distant light. That faint red glow isn't coming from something quiet and unchanging. It's the light of a star whose surface rises and falls in massive convection currents, whose outer layers constantly drift away into space. The brightness shifts in cycles that take years to complete. This is a star that dimmed dramatically in ways nobody expected, then brightened again, leaving behind questions scientists are still working to answer. Betelgeuse flickers, but not like a candle in the wind. Its changes unfold over months and years. The convection cells on its surface move so slowly that one complete cycle might take longer than a human generation. From our perspective, these motions appear almost still. An entire atmospheric upheaval on that star might span decades, playing out in slow motion compared to anything in our daily experience. This contrast between immense stellar activity and apparent steadiness offers something soothing about watching the night sky. The universe contains constant motion, but much of it unfolds gently on timescales that feel unhurried and patient. That patience becomes something we can share, at least for a few moments, simply by looking upward and remembering that not everything in existence operates at the frantic pace of human life. Perhaps you've noticed how different the night feels when you spend time outside, letting your eyes adjust to darkness. The world grows quieter, sounds become softer, the mind slows down, no longer pulled in multiple directions at once. You can sense rhythms larger than the ones governing daily routines. Stars like Betelgeuse invite this kind of stillness, reminding us of cycles measured not in minutes or hours, but in years, centuries, millennia. Even now, somewhere far beyond any telescope's reach, gas continues drifting outward from Betelgeuse. It cools as it expands, forming tiny dust grains that will eventually become part of something new. The star keeps pulsing, shifting, evolving in ways too slow for us to notice, from one night to the next. Yet the light reaching your eyes tonight carries the record of all those processes, encoded in subtle variations of brightness and color. That light has traveled across hundreds of light years to reach you. 600 years ago, when the photons now entering your eyes first left Betelgeuse, the world was completely different. Entire civilizations have risen and fallen during that journey. Countless generations lived their lives, each looking up at the same sky, unaware that the light they saw had begun its journey long before they were born. There's something gentle in this continuity. The sky doesn't rush from one moment to the next, doesn't hurry through its transformations. It unfolds at its own pace, indifferent to the passing of human days, steady in a way that feels reassuring. Even Betelgeus, unpredictable as it is, participates in this steadiness. Its recent dimming was dramatic by astronomical standards, but in the context of its entire lifetime, just one phase among many. This ongoing story continues unfolding whether we're watching or not. Astronomers will keep monitoring the star, measuring its brightness, mapping its surface, studying the clouds of material surrounding it. New instruments will reveal fresh details, models will improve. Some mysteries will find solutions while others emerge. This represents both the nature of science and, in a way, the nature of existence itself. Every answer opens up new questions. Every discovery reveals new paths to explore. But you don't need telescopes or equations to feel connected to this story. Simply knowing it's happening, that a star is slowly changing in the distance, can bring a sense of perspective about our place in the larger scheme of things. The same universe that shapes stars also shapes us. We're part of the same fundamental processes that govern stellar evolution. The slow loss of material from Betelgeuse participates in the same cosmic recycling that long ago made Earth possible. It's a quiet connection, subtle but real, linking us to processes playing out on scales we can barely imagine. Maybe that's why the night sky feels familiar, even though it's vast beyond comprehension. It's not entirely separate from us, but part of the same unfolding story. If you watched Betelgeuse night after night for years, you might notice subtle changes. Some evenings slightly brighter, others slightly dimmer. The variations would be small, almost imperceptible, but they'd be there, quiet reminders that even the most distant objects participate in motion and change. You don't have to watch every night to sense this motion, though it's enough to know it's happening, that the star continues, flickering and evolving long after we turn away. This thought can be strangely comforting. The universe continues its work regardless of human attention. Stars rise and set, light travels through space, gas drifts outward, dust forms, new stars are born. These processes unfold steadily, without hurry or interruption. There's calmness in such continuity, a sense that not everything needs to happen quickly, that some of the most important changes occur slowly, almost invisibly, over vast periods of time. This perspective can help the mind settle, letting go of the urgency that characterizes so much of daily life. As night deepens around you, you might imagine that distant red star still glowing, still changing, still sending its light across quiet darkness. Picture the slow rise and fall of its surface, vast currents of gas, clouds of dust drifting outward into space. West, currents of gas, clouds of dust drifting outward into space. West, currents of gas, clouds of dust drifting outward into space. Fast current of gas, west, west. None of it hurried, none abrupt, just steady, unfolding, patient and unbroken. Breathing becomes easier when nothing needs doing, when there's nowhere to go, when the mind can wander without direction. The night sky has always offered this kind of quiet companionship. For thousands of years, people have looked up at the same stars, finding comfort in their steady light, in the sense that beyond all earthly noise and motion, there exists a larger stillness.